Hello there and welcome to Science for Sleep, where we take some of the biggest questions in science, give them plenty of room to breathe and explore them slowly enough that falling asleep halfway through is not considered a failure. Tonight, we are looking at something very far away, very old, and rather inconvenient for cosmologists. It is known simply as the cold spot. That name makes it sound almost harmless. Perhaps a place in the refrigerator where the milk keeps freezing, or one side of the bedroom that never seems to warm up properly. But this particular cold spot covers an enormous patch of the sky, and it appears in the oldest light we can observe anywhere in the universe. That light is called the cosmic microwave background. It has been travelling through space for almost the entire history of the cosmos, carrying information from a time when the universe was only around 380,000 years old. Compared with the universe today, which is about 13.8 billion years old, that is extremely early. If the entire history of the universe were compressed into the lifetime of a person, the cosmic microwave background would be something like a photograph taken when that person was still a very small infant. And somewhere in that photograph is an unusually large, unusually cold patch. Scientists have studied it for years. They have checked the instruments. They have checked the data. They have compared observations made by different spacecraft. They have looked for enormous empty regions of space in front of it. They have considered unusual structures in the early universe. They have examined whether it might simply be a rare statistical accident. More adventurous ideas have even involved exotic physics and events that may have happened during the universe's earliest moments. And after all of that, the cold spot is still there. Not necessarily evidence that our understanding of the universe is wrong. Not necessarily proof of anything exotic, but stubborn enough that it has refused to become completely uninteresting. Which, in science, can be a surprisingly effective way to cause trouble. Before we get into exactly what this strange patch is, though, I'm curious about something much closer to home. Where are you listening from tonight? Perhaps you're in a city where there is still traffic passing outside your window. Perhaps you're somewhere quiet enough to see a few stars. Maybe it is very late where you are, or perhaps you've put this on in the middle of the afternoon and have decided that cosmological anomalies are as good an excuse for a nap as anything else. And if you happen to know, what does the sky look like where you are? Clear, cloudy, bright with city lights, completely dark. It is strange to think that no matter what your local sky looks like, beyond the clouds, beyond the atmosphere, beyond the stars that your eyes can see, the entire sky is filled with ancient microwave radiation. It is coming toward you from every direction. You cannot see it with your eyes. You cannot feel it against your skin. It does not make a sound. But suitable instruments can detect it, and when scientists turn those measurements into a map, they get one of the most important images ever made. It is a picture of the young universe, and hidden within that picture is our problem. If these slow journeys through science help you relax, or if you enjoy learning about the universe while allowing your brain to gradually forget that it is supposed to remain awake, you can give the video a like and subscribe to Science for Sleep. It helps the channel reach other people who may also enjoy spending their evenings thinking about extremely distant objects, instead of whatever they were probably supposed to be thinking about. For now though, get comfortable. There is no need to remember every number or every scientific term. The cold spot has managed to remain confusing despite the attention of professional cosmologists, so there is absolutely no pressure on anyone lying under a blanket to solve it tonight. The important thing is to understand why it caught their attention in the first place. To do that, imagine that someone hands you a photograph containing millions of tiny variations. Most of those variations are exactly the sort you expected to see. A little brighter here, a little dimmer there. Small differences spread across the whole image in a pattern that agrees remarkably well with a theory you have spent decades developing. Then, in one part of the photograph, you notice something odd. One region is different enough to make you look again. You calculate the probability. You change the way you analyse the image. You ask whether some foreground object could be interfering. You check another instrument. The feature remains. That is roughly the situation created by the cold spot. The cosmic microwave background is not perfectly uniform. If it were, modern cosmology would have a serious problem, because the small variations in this ancient radiation are extremely important. Those tiny differences are connected to slight differences in density in the early universe. Over immense stretches of time, gravity amplified those differences. Regions containing slightly more matter attracted more matter. Structures grew. Eventually, those early variations contributed to the formation of galaxies, clusters of galaxies, stars, planets, and, after an almost unreasonable amount of cosmic preparation, people lying in bed listening to videos about microwave radiation. So the mottled appearance of the cosmic microwave background is expected. The universe was not perfectly smooth. There are warmer-looking areas and colder-looking areas, although the differences are remarkably small. The average temperature of the cosmic microwave background today is only about 2.7 degrees above absolute zero, and the variations mapped across it are tiny fractions of a degree. The map is therefore not showing enormous regions that are comfortably warm beside regions that are dramatically frozen. The colours commonly used in pictures of the cosmic microwave background are exaggerated so that we can actually see the differences. Otherwise, you would mostly be looking at something extremely uniform and wondering whether the expensive satellite had forgotten to finish loading the image. Most of these temperature variations behave rather well. They form a statistical pattern that fits the standard cosmological model with impressive accuracy. That model, usually referred to as lambda CDM, describes a universe containing ordinary matter, dark energy, and an early period in which the tiny fluctuations that eventually became cosmic structure were established. It is not a theory constructed to explain one particular photograph. It successfully connects an enormous range of observations. That is part of what makes anomalies in the microwave background so interesting. When a model performs very well overall, an unusual feature presents scientists with several possibilities. Perhaps the feature is not actually unusual. Perhaps you have underestimated how often random patterns can look surprising. Perhaps something happened to the light after it began travelling toward us. Perhaps there is a problem with the measurement. Or perhaps the feature contains information about physics that the standard model does not fully describe. The difficult part is deciding which possibility deserves your attention. Humans are extraordinarily good at spotting patterns, including patterns that do not mean anything. Look at clouds for long enough, and you will eventually find a rabbit, a face, a sailing ship, or something that looks suspiciously like a potato. The universe provides considerably more data than a cloudy afternoon, which means scientists must be very careful about deciding when a strange-looking pattern is genuinely strange. If you examine a sufficiently large map and then choose the weirdest thing on it, that thing will naturally be weird. There has to be a weirdest thing. The cold spot suffers from precisely this problem. It is unusual, but determining exactly how unusual depends partly on the statistical method being used and on how the question is asked. This matters because phrases such as "scientists cannot explain it" can sound much more dramatic than the actual scientific situation. There are explanations, there are several of them. The problem is that none has achieved the pleasant status of being obviously correct. One possibility is that the cold spot is simply an unusually large fluctuation, produced by the same physics responsible for all the other temperature variations. In that case, there would be no mysterious object hiding behind it, and no missing ingredient in cosmology. It would be rare, but rare events happen. Shuffle a deck of cards properly, and the exact arrangement you receive is extraordinarily unlikely. You do not immediately conclude that another universe interfered with your deck. At least, hopefully not. Another idea is that something much closer to us affected the microwave radiation as it travelled across the cosmos. Light from the cosmic microwave background has spent billions of years passing through the evolving structure of the universe before reaching our telescopes. Along the way, it has encountered regions containing galaxies, clusters, dark matter, and enormous cosmic voids. A particularly large, underdense region along the line of sight could alter the energy of passing microwave photons slightly. This led scientists to investigate whether an enormous void might sit between Earth and the direction of the cold spot. And there really does appear to be an unusually underdense region in roughly that direction. For a while, that sounded encouraging. A mystery had appeared in the sky. Astronomers looked along the line of sight, and they found a giant region containing less matter than average. That is the sort of development that makes a theory feel as though it is about to become satisfyingly tidy. Unfortunately, the universe does not appear to feel any obligation to provide satisfying endings. Studies of the proposed supervoid have struggled to make it account for the full cold spot. The effect expected from the observed structure appears too small to produce everything seen in the microwave background temperature pattern. More recent analyses have made the simple supervoid explanation even harder to maintain, so there may be an enormous underdense structure in the right general direction, without that structure being sufficient to solve the problem. It is a bit like investigating why your kitchen is unusually cold, discovering that one window is open, and then calculating that the open window can explain only a small part of the temperature difference. Useful information, just not quite enough. Then we reach the explanations that attract rather more attention. Could something unusual have happened during the very early universe? Could the cold spot contain evidence of physics associated with inflation, the rapid expansion thought to have occurred during the universe's earliest moments? Could it be related to a cosmic defect, sometimes called a texture, created during a phase transition in the young universe? Could it somehow preserve evidence of an interaction involving another region of space-time? At this point, discussions of the cold spot sometimes make their way into headlines involving parallel universes, and parallel universes are very effective headline material. Possible statistical fluctuation remains mildly interesting, has never been especially good at attracting clicks. But we need to keep the different levels of certainty separate. The cold spot is real in the straightforward observational sense that an unusual low temperature feature appears in maps of the cosmic microwave background. NASA's WMAP mission detected it. ESA's Planck mission, using more precise observations, confirmed that the large cold feature was present in the CMB temperature data, rather than simply disappearing as the measurements improved. That does not mean every exotic interpretation is real. It means the feature being interpreted is not something we can casually dismiss as a smudge on one old map. Planck made this particularly interesting because Planck was designed to map the microwave sky with exceptional precision. Its results broadly strengthened the standard cosmological picture. Most of the cosmic microwave background behaved exactly as cosmologists hoped it would. And among all that success sat a handful of large-scale oddities. The cold spot was one of them. This is an important distinction. The cold spot is not a giant crack running through a failed theory of the universe. If it were, the situation would actually be simpler in some ways. A model that fails everywhere is easy to identify as a problem. Instead, cosmologists have something much more irritating. A model that works extremely well, accompanied by a few features that keep raising their hands from the back of the room. The cold spot is perhaps the most visually famous of those features. It lies in the southern part of the microwave sky, in the general direction of the constellation Eridanus. On common CMB maps, it looks like a dark blue region surrounded by warmer structure. Its angular size is enormous compared with familiar objects in our night sky. The moon spans roughly half a degree. The cold spot stretches across several degrees, and depending on exactly how its surrounding structure is defined, the broader feature can extend across something closer to 10 degrees. That does not directly tell us its physical size. The cosmic microwave background is not an ordinary surface floating at one particular modern distance, like the wall of a building. We are seeing radiation released throughout the universe when it became transparent, red-shifted and stretched during billions of years of cosmic expansion. Still, looking at the cold spot on a sky map gives you a sense of why it drew attention. It is not a tiny, suspicious pixel. It is a broad feature, and its internal temperature profile is part of what makes it unusual. There is a colder central region accompanied by surrounding structure, including a warmer ring-like area in some analyses. Scientists do not simply stare at this and decide whether it looks strange. They use statistical tools designed to identify patterns at particular angular scales. One of those tools helped bring the cold spot to attention in WMAP data during the early 2000s. We will get to that discovery properly later, because the story of how you decide that one patch of a universe-sized map is anomalous turns out to be almost as interesting as the patch itself. For now, there is a more basic puzzle. What are we actually looking at when we look at the cosmic microwave background? It is tempting to think of it as a photograph of the Big Bang. That description is common, useful, and slightly misleading. The cosmic microwave background does not come from the exact instant the universe began. For hundreds of thousands of years after the early hot universe, space was filled with a dense plasma. Light could not travel freely over enormous distances because photons repeatedly interacted with charged particles. The universe was more like a glowing fog than the transparent space we know today. As expansion continued, the universe cooled. Eventually, conditions changed enough for electrons and atomic nuclei to combine into neutral atoms. Once that happened, photons could travel much more freely. The light released from that transition has been travelling ever since. Cosmic expansion stretched its wavelength tremendously, shifting it into the microwave part of the electromagnetic spectrum. That ancient radiation now fills the sky. When a spacecraft such as WMAP or Planck maps it, we are effectively looking toward a boundary in our observable universe, beyond which ordinary light cannot show us earlier conditions directly. It is not a physical wall. It is a limit created by the history of matter and radiation. This is why the cold spot earns descriptions such as a scar from the early universe. Scar is not a technical term. Nothing tore the cosmic microwave background and then healed badly. But the metaphor captures the reason people care about it. If the feature originated at the surface from which this ancient light was released, rather than being produced by something along the way, then it could carry information from extraordinarily early cosmic conditions, possibly conditions connected to events far earlier than the 380,000-year point from which the microwave photons themselves escaped. The patterns in the CMB were influenced by the initial conditions of the early universe, so a strange enough pattern can send cosmologists looking backward toward inflation and the physics that created those initial variations. This is where the mystery becomes delicate. It is easy to move too quickly from unusual feature to unknown physics. Science has to travel the slower route. First, you ask whether the feature is statistically significant, then whether foreground contamination could produce it, then whether the analysis itself favours finding something unusual, then whether known structures between us and the CMB could account for it. Only after exhausting ordinary explanations does it become sensible to become seriously excited about extraordinary ones. The cold spot has survived long enough to keep all of those conversations alive. It has not forced cosmologists to abandon the standard model. It has not provided convincing evidence of another universe. It has not been cleanly explained by the enormous void found in its direction. It occupies a rather uncomfortable middle ground, interesting enough to investigate, ambiguous enough to argue about, and distant enough that nobody can simply send a spacecraft over for a closer look, which may be fortunate because the journey would make your current bedtime schedule somewhat difficult to maintain. There is something useful about mysteries like this. They reveal what science actually looks like when the answer is not available at the end of the page. From a distance, science can appear to be a collection of finished facts. The universe is this old. Light travels this fast. The cosmic microwave background has this temperature. But researchers usually work near the edges where measurements have uncertainty, explanations compete, and a result can remain unresolved for decades without anyone being able to honestly put a neat label on it. The cold spot lives in that territory. One group can calculate that its probability under the standard cosmological model makes it unusual enough to demand attention. Another can point out that once you account for how the feature was selected, the statistical surprise becomes less overwhelming. Observers can find a supervoid in roughly the right direction. Other researchers can calculate that the void cannot produce a temperature decrement large enough to explain the whole thing. Planck can confirm the temperature anomaly, while polarization measurements fail to deliver the decisive extra evidence everyone would have liked. And the result is not failure. It is simply an unsolved scientific question being gradually narrowed. That is what we are going to follow, not a hunt for the most dramatic possible explanation, and not an attempt to make the mystery disappear by calling it random. We're going to see why perfectly serious cosmologists can look at the same patch of microwave sky and disagree about how surprised we ought to be. We will see why empty space is not quite empty enough to provide an easy answer. We will eventually wander into inflation, cosmic structures, statistical probability, and a few ideas that sound suspiciously like science fiction until you discover that physicists have actually written equations for them. And now we have to return to a universe with no planets, no stars, no galaxies as we know them, and for a while, not even neutral atoms. Everything that would eventually become the structure around us was still encoded in tiny differences inside a hot, dense cosmic plasma, while light itself was struggling to travel anywhere at all. That last point is important, because when we look into space today, we are used to light behaving rather conveniently. A star releases photons. Those photons cross space. Some of them reach a telescope, and the telescope gives us information about the star. We can observe galaxies billions of light years away because space between us and those galaxies is mostly transparent. The early universe was not like that. Go back far enough, and the cosmos becomes so hot and dense that matter cannot settle into ordinary atoms. Electrons are moving freely, atomic nuclei are present, but electrons cannot remain attached to them for long because energetic radiation keeps knocking them loose. Instead of the familiar neutral matter around us today, you have an electrically charged plasma containing particles and enormous numbers of photons. A photon trying to cross this environment had a difficult commute. It would travel a short distance, encounter a free electron, scatter in a different direction, travel again, scatter again, and continue doing this repeatedly. Light existed everywhere, but it could not simply move across the universe in a straight line. The usual comparison is fog. If you switch on the headlights of a car in thick fog, the light does not travel cleanly to some distant object and return carrying a useful image. It scatters from droplets all around you. The early universe behaved somewhat similarly, except that instead of water droplets, photons were interacting primarily with charged particles. You could have had the finest telescope imaginable, and there would have been nothing distant for it to see through that plasma. Admittedly, having a telescope several 100,000 years after the Big Bang would have presented some additional engineering problems, starting with the lack of planets on which to put it. The important part is that the universe was opaque. Meanwhile, it was expanding. Expansion is one of those ideas that becomes misleading very quickly if we picture the Big Bang as an ordinary explosion. It was not matter exploding from one central point into previously empty space. Space itself was expanding, and matter and radiation were distributed throughout it. As the universe expanded, it cooled. After roughly 380,000 years, the temperature had fallen to around 3,000 Kelvin. That is still far hotter than any bedroom in which you would voluntarily try to sleep. But it was cool enough for an important change to occur. Electrons could finally remain bound to atomic nuclei. Hydrogen atoms formed in enormous numbers. Cosmologists call this period recombination, which is a slightly confusing name because there had not previously been neutral hydrogen atoms sitting around waiting to be recombined in the ordinary sense. Historical scientific terminology is sometimes like that. Once a name becomes established, everyone agrees to keep using it and quietly moves on. The formation of neutral atoms dramatically reduced the number of free electrons available to scatter photons. Suddenly, light could travel much farther. The cosmic fog cleared. Photons that had spent hundreds of thousands of years being scattered around were now able to stream through space. A vast number of those photons are still travelling through the universe today. Some are passing through your room right now. They have travelled for almost the entire age of the cosmos, passed through evolving galaxies and enormous empty regions of space, crossed our own galaxy, entered Earth's atmosphere, and continued on without the slightest concern about whether anyone happens to be awake to appreciate the effort. Those photons make up the cosmic microwave background. The phrase can sound technical, but each part of the name is fairly literal. It is cosmic because it comes from the universe as a whole, rather than from one nearby star or galaxy. It is microwave because cosmic expansion has stretched the wavelengths of the radiation until much of its energy now lies in the microwave region of the electromagnetic spectrum. And it is a background because it appears behind essentially everything else we observe, arriving from every direction in the sky. There is no particular point you can look toward to find the CMB. Turn around and it is there. Look north, south, toward the Milky Way, away from the Milky Way, above you, or through the Earth in the opposite direction, if you had an instrument capable of making that observation conveniently. The radiation surrounds us because every direction we look eventually reaches material that was part of that early transparent universe. This leads to a slightly unusual feature of astronomy. When we map the cosmic microwave background, we are not looking at one distant object. We are looking outward in every direction and backward in time. Because light takes time to travel, more distant observations show us the universe at earlier stages of its history. The Sun appears to us as it was a little over 8 minutes ago. A galaxy 10 million light-years away appears as it was 10 million years ago. The cosmic microwave background takes this principle almost as far as ordinary electromagnetic observations can go. Eventually, no matter which direction you look, you encounter the period when the universe became transparent. Astronomers call the effective boundary from which these photons last scattered the surface of last scattering. Again, it is not a solid surface. There is no shell sitting somewhere beyond the galaxies. It is more like looking into a cloudy atmosphere and seeing only as far as the layer where the fog becomes opaque. When you move, your visible boundary moves with you. An observer in a distant galaxy would also see a cosmic microwave background surrounding them, but the photons reaching that observer would have originated from different regions of the early universe. This detail is worth keeping in mind whenever you see the familiar oval maps of the CMB. The map is not a photograph taken from outside the universe. There is no camera hovering beyond creation, while someone politely asks the cosmos to fit into frame. It is an all-sky map made from our location. Astronomers take measurements from every direction around Earth and project the spherical sky onto a flat image, rather like turning a globe into a world map. Just as Greenland can look rather peculiar on some maps of Earth, the edges and shapes on a flat CMB map are affected by the chosen projection. The underlying measurements, however, are extraordinarily precise. The average temperature of the cosmic microwave background today is about 2.725 Kelvin, only a few degrees above absolute zero. That seems dramatically different from the roughly 3000 Kelvin temperature associated with the period when the radiation was released. Nothing had to refrigerate the photons. The expansion of the universe did the work. As space expanded, the wavelength of the radiation stretched with it. Longer wavelengths correspond to lower photon energies, so the once hot radiation gradually shifted through the electromagnetic spectrum until it became the faint microwave background we observe today. This stretching is called cosmological redshift. Visible light that is stretched moderately shifts toward the red end of the spectrum. Stretch it enormously, and it moves beyond visible red into infrared and eventually microwave wavelengths. The universe has expanded by roughly a factor of 1,000 since the CMB was released, and the wavelengths of those ancient photons have expanded with it. That makes the CMB a useful record of cosmic expansion, as well as a snapshot of early conditions. But if all the cosmic microwave background told us was that the young universe had once been hot, it would already be important. The real scientific treasure is in the fact that it is not perfectly uniform. Its temperature is nearly the same everywhere. Nearly. Once astronomers subtract several much larger effects and examine the background with sufficient sensitivity, they find tiny differences from one direction to another. One patch may be a few tens of millionths of a degree warmer than average, another may be slightly cooler. These temperature differences are called anisotropies. They are the little red, orange, blue and darker patches you see in famous maps, produced by missions such as COBE, WMAP and Planck. Those colours can create the wrong impression if you do not know what is being displayed. A red patch is not a region of the early universe that was blazing hot, while a neighbouring blue patch was frozen. The actual differences are tiny, around 1 part in 100,000 for the primary temperature fluctuations typically discussed. The colours are deliberately exaggerated so that our eyes can distinguish them. Without that enhancement, the image would look almost completely uniform. Scientifically impressive perhaps, but not especially helpful as a desktop wallpaper. Those tiny differences are essential because they tell us that the young universe was not perfectly smooth. Some regions were slightly denser than others. Gravity then had billions of years to work on those small differences. A region containing a little more matter exerted a little more gravitational attraction. It gathered additional matter. The contrast increased. Over immense periods, those initial irregularities helped develop into the large-scale structure we see today. Galaxies did not appear from a perfectly smooth universe without any starting differences. Neither did galaxy clusters. The great web of matter that now stretches across billions of light years can be traced back, in part, to fluctuations already present when the CMB was released. In that sense, the microwave map contains the early seeds of structure. Every galaxy visible through a telescope belongs to a much later stage of a process, whose initial conditions can be studied in this ancient radiation. That includes the Milky Way. It includes the material that formed the Sun. It eventually includes the carbon in your body, the calcium in your bones, and presumably whichever part of the brain decided that listening to cosmology at bedtime was a sensible plan. Scientists can extract an astonishing amount of information from these tiny temperature variations. To understand how, it helps to remember what the universe contained before recombination. Ordinary matter and radiation were tightly coupled. Gravity tried to pull matter into slightly denser regions. Radiation resisted that compression. When matter was compressed, the radiation pressure increased and pushed outward again. The result was a series of pressure waves moving through the hot plasma. They are often called acoustic oscillations. The word acoustic makes it sound as though the young universe was literally full of sound in the ordinary sense, and in a physical way it was. Pressure waves were travelling through the plasma. There would have been no human ears to hear them, of course, and any hypothetical listener would have had a very brief and unpleasant experience in a 3,000-degree environment. Still, these pressure waves mattered enormously. Different regions of the primordial plasma were caught at different stages of compression and expansion when the universe became transparent. Once photons decoupled from matter and began travelling freely, the pattern was effectively preserved in the radiation. That pattern is visible today. Cosmologists analyse it not merely by pointing at individual spots, but statistically. One important tool is the angular power spectrum. The name sounds like something designed specifically to discourage casual interest, but the idea is manageable. Imagine looking at the CMB map and asking how much temperature variation appears at different angular sizes. Are there strong patterns that span half the sky? Patterns several degrees across, smaller features, even smaller ones? The power spectrum measures how prominent fluctuations are at different scales. When scientists plot the result, they find a distinctive series of peaks. Those peaks contain information about the physics of the early universe. The position of the first major peak, for example, provides information about the geometry of the universe. The relative heights of different peaks help constrain the amount of ordinary matter and dark matter. Other details reveal information about the expansion history and about the initial fluctuations from which cosmic structure developed. This is one reason cosmologists became so excited about increasingly precise CMB measurements. You're not merely measuring an ancient temperature, you're using a pattern of tiny variations to estimate what the universe contains and how it evolved. That sounds almost unreasonable until you remember that physics links all of these processes together. Change the amount of ordinary matter and the primordial plasma behaves differently. Change the amount of dark matter and gravitational effects change. Alter the geometry of space and the apparent angular scale of ancient features changes. Different universes leave different statistical fingerprints in their microwave backgrounds. Our universe has left one particular fingerprint. The remarkable thing is how well that fingerprint agrees with the standard cosmological model. Measurements from the CMB have helped establish a universe that is approximately 13.8 billion years old and is dominated today by dark energy and dark matter, with ordinary atomic matter making up only a small fraction of the total cosmic energy budget. That alone is a wonderfully strange result. Everything we directly touch, every planet, star, gas cloud, cup of tea, alarm clock, and mildly judgmental houseplant belongs to the minority component. Most of the cosmic accounting appears to involve things we cannot see directly. The microwave background also gives physicists a way to investigate events much earlier than recombination. This might initially sound impossible. If the CMB is the oldest light we can directly observe, how can it tell us about anything before the light was released? Because the state of the plasma at recombination depended on earlier conditions. Suppose someone shakes a bowl of water and then photographs the surface a moment later. You did not directly photograph the hand that shook it, but the pattern of waves contains information about what happened beforehand. The early universe left information in a similar, though vastly more complicated way. One leading idea is cosmic inflation. According to inflationary models, the universe went through a period of extremely rapid expansion at a very early stage. Tiny quantum fluctuations could have been stretched to enormous scales during this process. Those fluctuations then became variations in density. Later, those density variations affected the primordial plasma. Eventually, their statistical pattern became imprinted in the cosmic microwave background. This is why scientists sometimes describe the CMB as a window onto physics at energies far beyond anything human laboratories can reproduce. We're observing radiation released 380,000 years after the Big Bang, but some features of that radiation may carry indirect information from unimaginably earlier moments. There is another property of the CMB that becomes important when scientists try to distinguish between competing explanations for unusual features. The radiation is polarized. Polarization describes the orientation of the oscillating electromagnetic field associated with light. Ordinary light can become polarized in familiar situations. Polarized sunglasses exploit this property by filtering certain orientations of incoming light. In the early universe, scattering processes produced a small polarized component in the cosmic microwave background. The resulting polarization pattern provides another layer of information about conditions around the time the radiation last scattered. This means cosmologists are not restricted to a single temperature map. They can compare temperature patterns with polarization patterns. That is extremely useful because different physical explanations may predict different relationships between the two. An unusual temperature feature caused by conditions at the surface of lost scattering might be expected to have a particular polarization signature. A feature produced much later, while CMB photons were travelling through the universe, might not produce the same one. This distinction will become especially relevant once the cold spot enters the story properly. Before scientists could search for such subtle clues, however, they first had to detect the cosmic microwave background at all. That happened in one of the more famous accidental discoveries in modern science. In the 1960s, radio astronomers Arno Penzias and Robert Wilson were working with a large horn antenna at Bell Telephone Laboratories in New Jersey. They encountered an unwanted background signal, It persisted. It did not seem to come from one specific direction. It did not conveniently disappear when they wanted it to. They investigated their equipment. They considered possible sources of interference. Famously, pigeons had been nesting in the antenna, leaving behind what was described in suitably polite technical language as a white dielectric material. The pigeons were removed. The antenna was cleaned. The mysterious noise remained. At roughly the same time, a group of physicists at Princeton University was preparing to search for exactly the kind of relic radiation that theoretical work on a hot early universe suggested should exist. Once the two groups became aware of each other's work, the significance of the persistent antenna noise became clear. Penzias and Wilson had detected the cosmic microwave background. The unwanted signal was not a local technical problem. It was radiation from the early universe. There is something reassuring about the fact that one of cosmology's greatest discoveries initially presented itself as an irritating bit of noise. Scientists had been trying to make the instrument quieter. The universe apparently had other plans. The discovery provided powerful evidence that the cosmos had once existed in a much hotter, denser state. Steady-state models of the universe, which proposed that the cosmos had no hot beginning of this kind, became increasingly difficult to maintain. But simply detecting the CMB was only the beginning. Researchers wanted to measure its spectrum precisely. They wanted to know whether it really had the thermal form predicted for radiation left over from the early universe. They also wanted to find the tiny variations that theories of structure formation said should exist. That required getting above Earth's atmosphere and building instruments far more sensitive than anything available to Penzias and Wilson. NASA's Cosmic Background Explorer, or COBE, launched in 1989, provided a major breakthrough. One of its instruments measured the CMB spectrum and found it to match an almost perfect blackbody curve. A blackbody is an idealized physical object whose radiation spectrum depends on its temperature. The CMB's agreement with this thermal spectrum was extraordinarily precise. It strongly supported the picture of radiation originating in a hot early universe. Then COBE detected something else: tiny temperature anisotropies. For the first time, scientists had convincing evidence of the slight variations from which later cosmic structure could grow. The map looked primitive compared with the images we have today. Large blotches covered the sky. The resolution was limited, but those blotches were enough to change cosmology. They showed that the early universe contained the irregularities needed to produce the complicated universe around us. The next major step came with NASA's Wilkinson Microwave Anisotropy Probe, better known as WMAP. Launched in 2001, WMAP measured the microwave sky with much greater resolution and sensitivity. Instead of merely establishing that fluctuations existed, it could map their structure across the sky in detail. WMAP transformed the CMB from a broad confirmation of the Big Bang into a precision tool for cosmology. The age of the universe could be constrained more accurately. The geometry of space could be tested. The proportions of different cosmic components could be estimated. The statistical pattern of primordial fluctuations could be compared with predictions from inflation. Later, ESA's Planck spacecraft pushed those measurements still further. Planck observed the sky across 9 frequency bands, helping researchers separate the primordial microwave signal from radiation produced by our own galaxy and other foreground sources. Its detectors measured temperature differences of only a few millionths of a degree. The resulting map is filled with fine structure. At first glance, it can look random. There are countless warm and cool regions scattered across the sky with no obvious arrangement. But statistically, the map is highly organized. The sizes and strengths of the fluctuations closely match what cosmologists expect from the standard model. This agreement is one of the great successes of modern cosmology, and it creates an important problem for anyone hunting anomalies. When a theory explains almost everything in a data set, how seriously should you take the few features that look different? You cannot simply declare every unusual patch to be new physics. Random fields naturally contain unusual-looking areas. Foreground subtraction is difficult. Statistical methods can emphasize some structures more than others. Our own galaxy is bright at microwave frequencies, and removing its contribution requires careful modelling. Radio sources, dust, and other emissions must also be separated from the primordial background. Even the motion of our solar system relative to the CMB produces a large temperature pattern across the sky, making one direction appear slightly hotter and the opposite direction slightly colder. That dipole effect must be removed before scientists study the much smaller primordial fluctuations. There are layers of correction between the raw microwave sky and the clean-coloured maps that appear in cosmology books. This makes the agreement between independent missions particularly valuable. COBE saw the broad anisotropies. WMAP mapped them in much greater detail. Planck produced the most precise full sky temperature map of the CMB yet made. Across different instruments, different observing strategies, and different frequency ranges, the basic cosmological picture survived. So did several peculiar large-scale features. That is where our original problem begins to return. Most temperature fluctuations in the CMB are exactly the kind of fluctuations cosmologists expect. There should be hot regions. There should be cold regions. If every patch had exactly the average temperature, the map would be far more surprising than anything we actually observe. The question is not whether a cold area exists. The question is whether one particular cold area is too large, too deep, or otherwise too unusual to fit comfortably among the ordinary fluctuations. That is a much harder question. You need a statistical model. You need simulations of possible microwave skies. You need a way to search those skies without accidentally designing your search around the feature you have already noticed. Then, you compare what our universe produced with the range of patterns expected by chance. Early CMB maps did contain visible cool regions, but the limited resolution made it difficult to say much about unusual structures at particular scales. WMAP changed that. Once researchers had a detailed all-sky map, they could apply mathematical techniques designed to identify features of different sizes and shapes. And in the southern celestial sky, toward the constellation Eridanus, one region began attracting attention. It was not simply the coldest individual pixel. That would not have been especially meaningful. It was a broad structure that looked unusual when the map was examined at certain angular scales. Researchers filtered the CMB data in a particular way, and found that this region stood out from most of what appeared in simulated skies, based on the standard cosmological model. The more carefully they looked, the more interesting the question became. Was this just the kind of rare fluctuation that eventually has to occur somewhere when you map an entire sky? Was there an unknown problem in the data? Could foreground radiation be fooling the analysis? Had something between us and the last scattering surface changed the energy of those ancient photons? Or was the strange patch already present when the cosmic microwave background began its journey toward us? Once researchers had a detailed all-sky map, the next problem was deciding whether every pattern on that map was behaving the way the standard cosmological model said it should. That is harder than it sounds. A map of the cosmic microwave background contains enormous numbers of temperature measurements. Some areas are warmer than average, others are colder. There are small features, broad features, clusters of features, and shapes that can look surprisingly deliberate even when they were produced by random fluctuations. If you stare at enough noise, eventually something will look important. Scientists therefore needed more than a suspicious blue patch on a screen. They needed mathematical tests capable of asking whether the pattern of temperature fluctuations across the entire sky behaved like the kind of random field predicted by the standard model. That was one of the reasons the first-year data from NASA's Wilkinson Microwave Anisotropy probe attracted so much attention when they were released in 2003. WMAP was a major improvement over COBE. Its maps had far better angular resolution and sensitivity. revealing structure in the microwave background on much smaller scales. The broad fuzzy variations detected by COBE became a detailed field of hot and cold fluctuations. For cosmologists, it was an extraordinary data set. For statisticians, it was also an invitation to start looking for trouble. The standard cosmological picture predicts that the primordial temperature fluctuations should be very close to what mathematicians call Gaussian. Gaussian does not mean smooth, symmetrical, or boring when applied to a sky map. It refers to the statistical distribution and relationships of the fluctuations. A familiar example of a Gaussian distribution is the bell-shaped curve. Many values gather around an average, while increasingly extreme values become progressively less common. In the CMB, the idea is more complicated because researchers are dealing not only with individual temperatures, but also with how fluctuations are arranged across different positions and angular scales. Still, the general expectation is clear. If the simplest inflationary models are broadly correct, then the primordial CMB should behave approximately like a Gaussian random field. Most of it does. That point is worth repeating because the cold spot can sometimes be presented as though WMAP revealed an obviously broken universe. It did not. The overwhelming majority of the microwave sky behaved remarkably well. The power spectrum fit cosmological predictions. The statistical properties were largely consistent with Gaussian fluctuations. Then researchers began applying more specialized tests. One group included physicists Patricio Vielva, Enrique Martínez González, Rafael Barreiro, José Luis Sanz, and Luis Cayón. They used a mathematical technique involving something called the spherical Mexican hat wavelet. This is one of those scientific names that sounds substantially more festive than the calculation itself. The Mexican hat part comes from the shape of the mathematical function. If you plotted a two-dimensional version, it would have a central region surrounded by a broader area of opposite sign, producing something resembling a sombrero. The word spherical is there because the sky surrounds us. A technique designed for a flat image needs to be adapted when the data live on a sphere. The important thing is not the shape of the hat, it is what a wavelet allows you to do. Suppose you have a photograph filled with objects of different sizes. You might want to search for broad structures without being distracted by tiny details. Or perhaps you want to isolate small structures while ignoring the broad background. A wavelet acts rather like a mathematical filter that emphasizes features at a chosen scale. Researchers can apply the filter at several scales and ask what the map looks like each time. Very small-scale noise may become less important when examining large structures. Broad patterns may disappear when the filter is tuned to small features. This makes wavelets useful for finding unusual structures that would not necessarily stand out in an ordinary visual inspection. Vielva and his colleagues applied the spherical Mexican hat wavelet to the first-year WMAP data. They examined the coefficients produced by the filtering process and calculated statistical quantities, including skewness and kurtosis. Skewness measures whether a distribution is asymmetrical. Kurtosis is related to how strongly the distribution produces unusually extreme values compared with a Gaussian expectation. You do not need to remember the definitions. The useful point is that these measurements allowed the researchers to ask whether the filtered WMAP sky behaved like thousands of simulated skies generated under the assumption of Gaussian primordial fluctuations. At most scales, nothing especially alarming happened. Then, at wavelet scales around 4 degrees, corresponding to structures roughly 10 degrees across on the sky, the statistics began to look unusual. The kurtosis was higher than expected. When the researchers divided the sky into hemispheres, the effect appeared especially strongly in the southern galactic hemisphere. The northern hemisphere looked broadly compatible with the Gaussian simulations. The southern side did not behave quite so politely. In their initial analysis, the probability of obtaining a kurtosis value at least as extreme as the one seen in the data was reported at roughly 0.4% for the full sky test at the relevant scale, and around 0.1% in the southern hemisphere under the particular analysis they performed. Those numbers sound dramatic. They also require caution. A probability of 0.1% does not automatically mean there is a 99.9% chance that new physics has been discovered. Statistical significance in cosmology rarely works that simply. Researchers test different scales. They may examine different statistics. They divide the sky in different ways. They sometimes notice something unusual, and then design a more focused test around it. Every additional opportunity to find an anomaly increases the chance that one of the tests will eventually produce an unlikely result. If you roll a die once and get 6, nothing remarkable has happened. If you announce beforehand that you will roll a 6 10 times in a row and then do it, people may start inspecting the die. But if you perform thousands of different experiments and report only the most surprising sequence afterward, the interpretation becomes more complicated. This is sometimes described through the look elsewhere effect. The cold spot would spend much of its scientific life living with exactly this problem. How surprising is it really? That depends partly on whether the question was defined before anyone saw the answer. Still, the wavelet result was interesting enough to investigate. The next obvious question was whether the unusual statistics were being caused by many mildly strange parts of the sky, or by one particularly extreme feature. Researchers Maria Cruz, Enrique Martinez Gonzalez, Patricio Vielva, and Luis Callon examined the WMAP data more closely. The answer turned out to be unusually concentrated. Most of the non-Gaussian signal could be traced to a single large cold region. Its position was approximately galactic longitude 209 degrees and galactic latitude -57 degrees. That places it well away from the bright central plane of our Milky Way, in the general direction of the constellation Eridanus. Today, that region is what we usually mean when we talk about the CMB Cold Spot. The researchers compared its properties with 10,000 simulated Gaussian CMB skies. Under their particular wavelet analysis, only around 0.2% of the simulations contained a cold spot with comparable properties. Again, that did not settle the statistical argument, but it made the feature difficult to ignore. It also revealed why simply looking for the coldest pixel would have missed the point. The cold spot was unusual because of its structure over a broad angular scale. The central area was colder than average across a large region, and the filtered signal had a distinctive profile. Depending on exactly how the boundary is defined, descriptions of the cold spot size vary, but the prominent structure spans several degrees, and its broader wavelet signature is roughly 10 degrees across. For comparison, the full moon occupies about half a degree of sky. You could therefore place many full moons across the angular width of the feature. Of course, angular size does not tell you that the cold spot is a physical object sitting at one particular distance. That distinction would become extremely important later. At this stage, researchers had found an unusual pattern in ancient radiation. They did not yet know whether the cause was primordial, something that happened to the radiation during its journey, an issue with the measurements, foreground contamination, or merely an unlikely but legitimate random fluctuation. So they started with the least exciting possibilities. That is usually a good habit in science. Before proposing an event from the first moments of the universe, it is worth checking whether your telescope has done something peculiar. WMAP did not observe the sky at only one microwave frequency. It used several frequency bands. That was crucial because many sources of unwanted radiation have frequency-dependent signatures. Our own Milky Way emits microwaves, dust contributes, charged particles moving through magnetic fields produce synchrotron radiation, free electrons interacting with ions create free emission. There are also radio sources outside the galaxy. All of these foregrounds can interfere with attempts to isolate the primordial CMB. If the cold spot were caused mainly by an ordinary foreground source, its appearance might change significantly from one WMAP frequency band to another. Researchers therefore examined the relevant maps separately. The unusual cold feature remained. In the early analyses, the non-Gaussian pattern appeared consistently in the Q, V and W frequency data used for cosmological studies. That reduced the likelihood that a simple frequency-dependent foreground was responsible. They also tested combinations designed to emphasize instrumental noise and systematic errors, rather than the common sky signal. Those tests did not reproduce the anomaly in the same way. This mattered. A flaw in one detector might produce an artificial cold region. A calibration problem might leave a pattern. The process of scanning the sky might introduce a systematic artifact. But if multiple independent detector channels observing at different frequencies all see the same feature in the same location, a simple instrumental explanation becomes less convincing. There was another issue. The Milky Way is messy. When cosmologists analyze the CMB, they often mask regions of the sky where foreground contamination is especially severe, particularly around the galactic plane. Changing the mask can potentially change statistical results. Perhaps the apparent anomaly depended on exactly which areas had been removed. Different studies tested this. The signal persisted under a variety of reasonable masking choices. The cold spot was also positioned far enough from the galactic plane that the most obvious forms of galactic contamination were not easy explanations. None of this proved that the feature came from the early universe. It merely closed several convenient exits. Then there was the possibility that the anomaly arose because cosmologists had used slightly incorrect values for parameters when generating their simulated skies. If you compare reality with the wrong theoretical simulations, reality may look strange for reasons that have nothing to do with exotic physics. Researchers varied the cosmological assumptions within their uncertainties. The basic unusual wavelet signal remained difficult to erase. Other teams began examining the same data with related methods. Some reproduced evidence for unusual statistics in the southern sky. Others emphasized that the statistical interpretation depended strongly on the chosen method. This was the beginning of a pattern that continues in cold spot research. The observational feature itself is not especially controversial. The argument concerns what the feature means and how unlikely it truly is under the standard model. Those are very different questions. Imagine shuffling a deck of cards and dealing yourself a particular hand. The hand exists, nobody disputes that. The harder question is whether the hand is surprising enough to suspect something unusual about the shuffle. To answer that, you must specify what would have counted as surprising before seeing the cards. If you receive 5 cards of the same suit, the criterion is straightforward. If you receive a random-looking collection and then announce that this exact combination is incredibly unlikely, you're technically correct but not scientifically impressed. Every exact combination was incredibly unlikely. The cold spot is much more sophisticated than that example, but the statistical concern is related. Researchers noticed it using a specific wavelet statistic at particular scales. How much should the significance be reduced because multiple scales and statistics could have produced an interesting anomaly? What if a different kind of unusual structure elsewhere on the sky would have attracted equal attention? This is the a posteriori problem. A posteriori simply means after the fact. If you choose the test after seeing the data, you have to account for that choice when deciding how surprising the result is. Cosmologists have spent years debating how much this reduces the cold spot's significance. Depending on the statistic, mask, simulations, and treatment of the look elsewhere effect, you can obtain different estimates. This is why careful scientists tend not to describe the cold spot as a discovery of new physics. They describe it as an anomaly. That word is useful. It says that something in the data looks unusual relative to an expectation, without pretending that the cause is known. The WMAP team itself was cautious about claims of primordial non-Gaussianity. WMAP's broader statistical analyses found the CMB to be very close to Gaussian overall. That remains important. A single unusual feature does not mean the entire microwave sky has abandoned Gaussian statistics. In fact, when Cruz and colleagues removed the cold spot region from their analysis, much of the excess kurtosis that had originally triggered attention disappeared. The remaining map became compatible with Gaussian expectations under that test. In one sense, this made the cold spot even more interesting. The odd statistical signal was not spread diffusely across the southern hemisphere. One place was doing most of the work. There is something almost unfair about that. You construct a satellite, map the oldest light in the universe, process millions of measurements, compare the entire sky with sophisticated statistical models, and one patch in Eridanus becomes the reason everyone starts arguing. Naturally, scientists wanted more data. WMAP continued observing. 1 year became 3 years, 3 became 5. Eventually the mission produced 9 years of measurements. If the cold spot had been a temporary statistical artifact created mainly by noise in the first-year data, improved observations could have weakened it. They did not make it disappear. The feature remained visible in later WMAP maps. Analyses using additional years of observations continued to find the same broad cold region. That did not automatically increase its statistical significance in a simple way, because large angular scale CMB measurements are affected by something called cosmic variance. Cosmic variance is an unusual limitation. Most experimental uncertainty can, in principle, be reduced by collecting more data. Measure something longer and noise decreases. Build a better detector and precision improves. But when studying the larger structures in the CMB, we have only one observable sky. We cannot ask for another independent universe, map its microwave background, and compare the two. At least the astronomy funding agencies have so far been reluctant to approve that proposal. The largest angular patterns are based on a limited number of independent modes across our single sky. That creates an irreducible statistical uncertainty. More sensitive instruments help with measurement noise and foreground separation, but they cannot give us multiple independent realizations of the universe. This is one reason large-scale CMB anomalies are so frustrating. You can measure the same feature better. You cannot easily determine whether our entire observable universe simply happened to receive an unusual random configuration. By the late 2000s, the cold spot had attracted a growing list of possible explanations. Some researchers argued that it could still be an ordinary Gaussian fluctuation that looked more impressive because of the way it had been selected. Others proposed that a large structure between us and the CMB might have altered the temperature of photons passing through it. Still others considered much more exotic possibilities involving unusual physics in the early universe. Before those ideas could be taken too seriously, though, there was an obvious test approaching. A new spacecraft was going to map the cosmic microwave background with greater sensitivity, improved angular resolution, and broader frequency coverage than WMAP. That spacecraft was Planck. The European Space Agency launched Planck in May 2009. Like WMAP, it was designed to measure tiny variations in the microwave background across the entire sky. Planck observed 9 frequency bands ranging from 30 to 857 GHz. That broad frequency coverage gave researchers a powerful way to separate the primordial CMB from foreground radiation produced by the Milky Way and other astrophysical sources. Its measurements would eventually produce the most detailed full-sky maps of the CMB temperature anisotropies made to that point. For the cold spot, this represented a critical independent check. WMAP had found the feature. WMAP's later observations had retained it. But WMAP used the same basic spacecraft and instrument family throughout its mission. If some subtle WMAP-specific systematic effect had survived all the earlier tests, an entirely different mission might reveal it. Planck used different instruments, different detectors, different frequency coverage, different data processing methods. If the cold spot disappeared in Planck data, the mystery could become an engineering story. When Planck's first major cosmological results were released in 2013, the cold spot was still there. ESA specifically highlighted it among the large-scale anomalies that had originally been seen by WMAP and were now confirmed in Planck's higher precision measurements. the broad low-temperature region remained in the same part of the sky. This was an important moment in the history of the anomaly. It became much harder to blame the cold spot on a simple WMAP instrument problem. Planck's observations also strengthened confidence that the feature was genuinely present in the CMB temperature sky rather than being produced entirely by ordinary foreground contamination. In other words, the strange patch had survived a second spacecraft. That sounds more decisive than it actually was. Planck confirmed the feature. It did not confirm an exotic explanation for the feature. Those two statements are easy to mix up. When ESA said that Planck had confirmed the cold spot, it meant the unusual temperature structure identified in WMAP was also present in the independent Planck data. It did not mean Planck had established that the cold spot was a scar from another universe, evidence of a cosmic texture, or proof that the standard model had failed. The statistical situation remained complicated. Planck's global tests showed that the CMB was broadly consistent with Gaussianity and statistical isotropy, particularly across the scales where the standard cosmological model performs best. At the same time, several large angle anomalies persisted. The cold spot was among them. Planck researchers used multiple statistical approaches. They examined temperature profiles. They studied peak statistics. They measured quantities such as kurtosis. Again and again, the region emerged as unusual in particular analyses. Yet researchers also emphasized the difficulty of assigning a clean probability to anomalies chosen after inspecting the data. This created an odd scientific situation. The better the maps became, the less plausible, simple observational mistakes looked. But better maps could not automatically tell researchers whether the cold spot represented new physics, or simply an uncommon realization of known physics. It was definitely on the sky. That was not the same as saying it definitely should not be there. One useful way to think about the problem is to imagine generating enormous numbers of simulated universes. Each simulation follows the same basic cosmological rules. Each receives a different random arrangement of primordial fluctuations. Most simulated microwave skies look ordinary. Some contain surprisingly large hot areas. Some contain broad cold areas. A few may produce features that look remarkably similar to the real cold spot. The question is how often? That sounds straightforward until you ask what similar means. Same minimum temperature, same radius, same warm ring around it, same wavelet coefficient, same location relative to other large-scale anomalies, same profile when averaged in circles around the center. Every definition changes the probability. Choose the definition because you already know what the real cold spot looks like and the statistical penalty returns. This is why you may encounter different numbers for the cold spot's significance. One paper might describe a probability below 1% for a particular statistic. Another may conclude that after accounting properly for selection effects, the anomaly is less significant. Neither result necessarily means the other team made a mistake. They may simply be asking slightly different questions. There was also a deeper reason cosmologists cared about whether the CMB fluctuations were Gaussian. Inflation, in its simplest forms, naturally produces fluctuations that are extremely close to Gaussian. A convincing detection of primordial non-Gaussianity could therefore provide information about the physics of inflation. It might point toward more complicated inflationary fields, interactions, or entirely different early universe mechanisms. That means an unusually non-Gaussian feature in the CMB is potentially valuable. But potential value is precisely why the standards of evidence must be high. If one strange region is going to tell us something fundamental about the first fraction of a second after the Big Bang, we want to be very sure it is not the cosmological equivalent of seeing a face in a piece of toast. The cold spot survived the obvious checks. That was the part nobody could easily dismiss. It appeared across relevant microwave frequencies. It was not comfortably explained by known galactic foregrounds. It remained through improved WMAP datasets. It appeared again in Planck. It continued to stand out under several statistical methods. At the same time, it existed in a universe where rare random fluctuations are allowed. The standard model does not predict that every patch of the microwave sky should look equally ordinary. Quite the opposite. A random field must contain extremes. There will always be a hottest region. There will always be a coldest region. There will always be some feature that ranks first on whichever list of cosmic oddities you decide to make. The real issue was whether this particular extreme went beyond what a reasonable realization of the standard model should produce. That question could not be settled by measuring the temperature map again. Researchers needed to ask what could physically create a feature with this size and temperature profile. If it was not primordial, perhaps something happened to the CMB photons after they left the surface of last scattering. Those photons have not travelled through an empty universe. Between that ancient plasma and our telescopes lies almost 13.8 billion years of evolving cosmic structure. Galaxies formed, clusters grew, dark matter gathered into vast networks, huge regions became comparatively empty. The gravitational potentials through which CMB photons travel changed as the universe evolved. Under the right circumstances, passing through one of those structures can slightly alter a photon's energy. That gave researchers a much more conventional possibility than collisions between universes. Perhaps there was simply something enormous sitting in front of the cold spot. Astronomers began mapping galaxies in its direction, and they found something. Along roughly the same line of sight lay an unusually large underdense region, a place containing fewer galaxies and less matter than average, a supervoid. For a while, this looked like exactly the kind of answer the cold spot needed. A strange microwave feature had been found in one direction. A very large cosmic void appeared in front of it. Known physics provided a mechanism through which evolving gravitational structure could affect CMB photons. The pieces appeared to be moving into position. Then researchers started calculating whether the numbers were actually large enough. That was when the apparently simple explanation became much less comfortable, because finding a giant empty region in the correct direction turned out to be only the beginning of the problem. Finding the cold spot was one thing. Deciding whether it deserved to be called a mystery was much harder. By the time Planck confirmed that the same large, low-temperature feature seen by WMAP was genuinely present in the cosmic microwave background, the easiest explanations had started to disappear. It was not confined to one detector. It was not restricted to one observing frequency. It remained after different methods were used to remove radiation from our own galaxy. It appeared in data from 2 independent space missions using different instruments. So the question changed. Scientists were no longer asking whether the cold spot existed. They were asking whether it should exist. That sounds like a small distinction, but it sits at the centre of the entire debate. The standard cosmological model does not predict a perfectly even microwave sky. It predicts fluctuations. Some regions should be warmer than average. Others should be colder. A few should be unusually warm or unusually cold simply because random processes occasionally produce extreme results. If you scatter enough points randomly across a page, somewhere there will be an unusually empty patch. Somewhere else there will be an unusually crowded one. Neither requires new physics. The CMB works in a much more complicated way, but the principle is similar. So a cold region, even a very cold region, is not automatically mysterious. The cold spot became interesting because several characteristics appeared together. It was unusually large. It had an unusually low central temperature. Its temperature changed with distance from the centre in a way that researchers described as unusually steep. And when certain mathematical filters were applied at angular scales of several degrees, it produced a stronger response than almost all comparable regions generated in simulations of ordinary Gaussian CMB skies. That combination is what kept it alive as a scientific problem. Consider the size first. On the sky, the main cold spot structure occupies several degrees, while the broader feature identified by wavelet analysis extends across roughly 10 degrees depending on exactly how researchers define its boundary. The full moon is only about half a degree across, so this is not an obscure, one pixel imperfection buried in a complicated dataset. The region covers a substantial piece of the microwave sky. That does not mean there is necessarily one enormous physical object corresponding directly to that angular size. The CMB is a projected view of conditions in the early universe, and later structures can also alter the radiation before it reaches us. Still, angular scale matters because the standard cosmological model predicts how much variation should occur on different scales. Small fluctuations are common. Large fluctuations also exist, but there are fewer independent large regions across the sky. A very unusual structure spanning many degrees therefore attracts attention more quickly than one strange pixel among millions. The cold spot is also not simply a broad region that happens to average slightly below the mean temperature. Its profile is part of the problem. Move outward from its coldest area, and the temperature changes relatively sharply. Analyses of the region have also identified surrounding warmer structure. The exact appearance depends on the smoothing scale and filtering technique being used, but the general result survives. This is a distinctive large-scale feature, rather than a collection of unrelated cold pixels that accidentally sit near one another. ESA later described it as a large low-temperature region with an unusually steep temperature profile. That wording is important. Being cold is expected. Being large is less common. Being large, cold, and shaped unusually begins to make statisticians uncomfortable, not terrified. Cosmologists do not normally flee laboratories when a p-value becomes small, but uncomfortable enough to keep calculating. The original wavelet studies produced probabilities below 1% for finding comparable features under particular assumptions. Some analyses found values around a few tenths of 1%. The Planck 2013 analysis also found that the cold spot produced unusually extreme statistics at several wavelet scales, with tail probabilities around 0.1% for some tests. Read quickly, numbers like that can sound almost decisive. A 0.1% probability seems to imply something extraordinary. But this is where the cold spot becomes a lesson in why statistical reasoning is much less straightforward than saying, only one chance in 1,000, therefore aliens, or another universe, or a crack in the Big Bang. Scientists have to ask what that probability actually represents. Suppose researchers had predicted before WMAP launched that a circular cold region would appear at one exact position in Eridanus, with one exact angular size, one exact temperature profile, and one exact wavelet signature. Then WMAP observed precisely that feature. That would be astonishing. There would be very little freedom to explain the result as something selected after looking at the data. But that is not what happened. Researchers examined a complex all-sky map using different statistical tools and different angular scales. An unusual feature emerged from that analysis. Once it was noticed, scientists naturally began asking more specific questions about it. How cold is it? How large is it? How unusual is its surrounding ring? How rare is its wavelet coefficient? How many simulated skies contain anything similar? Each of those questions is legitimate. The difficulty is that the target was already visible. This introduces what statisticians sometimes call an a posteriori selection problem. You notice something strange first, then calculate how unlikely that particular strange thing is. The danger is that almost any sufficiently complicated random data set contains something that looks highly improbable once you describe it precisely enough afterward. Imagine inviting 1,000 people into a hall and recording their birthdays, heights, first names, occupations, shoe sizes, and hometowns. Eventually you may discover that one person has exactly the same birthday, height, first initial and shoe size as someone standing 3 rows away. You calculate the probability of that exact combination and discover that it is extremely small, but you did not predict the combination beforehand. You searched a large data set containing many possible coincidences and selected the most interesting one afterward. That changes how impressed you should be. The cold spot is not merely a coincidence of birthdays and shoes, but the statistical issue is similar. How many different kinds of anomaly would have attracted attention if they had appeared instead? Perhaps an unusually large hotspot, perhaps a ring, perhaps a long linear feature, perhaps an unusual collection of smaller spots, perhaps an asymmetry elsewhere on the sky. The more possible patterns you would have considered interesting, the greater the probability that one of them will eventually appear. This is why different studies have reached different conclusions about how significant the cold spot really is. Some statistical methods make it look highly unusual. Others reduce its significance considerably once they account for the way the feature was selected. Researchers have even disagreed over which filters provide the most appropriate way to quantify it. The spherical Mexican hat wavelet, which helped reveal the anomaly, is particularly sensitive to structures resembling a cold center surrounded by warmer material. Other kernels do not always make the cold spot look as exceptional. Is that evidence that the original result was exaggerated? Possibly. Or it may simply mean that some filters are better than others at detecting this specific type of structure. This is one reason the argument has lasted so long. There is no universally accepted single number called the probability that the cold spot is mysterious. Science would be much easier if unusual objects came with labels. Normal random fluctuation. New physics. Please check foreground subtraction. Unfortunately, nature does not appear to provide those. There is also something called cosmic variance, which makes the situation especially awkward. On the larger scales, we have only one observable universe. We can measure its microwave background more accurately, but we cannot obtain another completely independent CMB sky for comparison. Computer simulations help. Researchers generate enormous numbers of artificial microwave skies using the statistical properties predicted by the standard model. They then apply the same analysis used on the real data. If features resembling the cold spot appear frequently, the real feature becomes less surprising. If they almost never appear, interest rises. Yet simulations cannot remove the fundamental fact that we possess one actual realization of the universe. Perhaps ours simply contains a rare fluctuation. A 1 in 1,000 event does not violate a model. It occurs once every 1,000 trials on average. Some universe has to be the one containing it. We happen to live in a universe where at least one person has been struck by lightning more than once. Someone has probably won an extremely unlikely lottery combination, and occasionally a piece of toast lands butter side up. Low probability is not the same thing as impossibility. That is why cosmologists are careful with the cold spot. It could be rare and completely ordinary at the same time. The problem is deciding how rare an event must become before looking for additional physics is justified. Planck made that question more serious because it removed some of the uncertainty about whether the feature was observational. When WMAP first showed several large-scale anomalies, scientists could reasonably wonder whether subtle instrumental effects or imperfect foreground removal were involved. Planck observed the microwave sky differently and with greater precision. The same cold spot appeared. ESA's analysis concluded that the large temperature anomalies were clearly present in the cosmological signal rather than in the instrument noise. That eliminated a very convenient explanation. If your strange measurement disappears when a better instrument is built, everyone can go home early. If the better instrument reproduces it, someone normally has to stay late. There was another reason the cold spot attracted attention. It was not the only odd large-scale feature in the CMB. Researchers had also reported an apparent asymmetry between opposite hemispheres of the sky. There was less temperature variation on very large angular scales than the best-fitting standard models seemed to predict. The lowest multipoles showed curious alignments. Some of these effects became associated with the memorable, if slightly theatrical phrase, axis of evil. The cold spot belonged to a broader collection of features that seemed to appear preferentially on the larger scales. This raised a tempting possibility. Maybe these were not independent accidents. Perhaps several anomalies were symptoms of one deeper effect. If the early universe behaved slightly differently from the simplest assumptions used in the standard model, several unusual large-scale patterns might appear together. That possibility has been investigated extensively. it has not produced a convincing unified explanation. Some anomalies may be related, others may not be. Their statistical significances change depending on the analysis. Several become weaker when researchers account carefully for selection effects. The safest conclusion is that the large-scale CMB contains a number of curious features without a demonstrated common cause. That makes the cold spot more interesting, but it does not turn the entire microwave sky into evidence against modern cosmology. In fact, one of the strangest things about the situation is how well the standard model works everywhere else. Planck measured temperature fluctuations across an enormous range of angular scales. It measured polarization. It measured gravitational lensing of the CMB. The resulting data provide excellent agreement with a relatively simple 6-parameter lambda CDM model. The same framework successfully describes the acoustic peaks in the microwave power spectrum, the approximate age and composition of the universe, and a large collection of other observations. So cosmologists are not dealing with a theory that has collapsed. They are dealing with a theory that works annoyingly well while leaving a few marks around the edges. That changes the burden of proof. If your model fails in 50 independent ways, replacing it becomes attractive. If your model succeeds in thousands of measurements and produces one unusual patch, the unusual patch has to work much harder before you rebuild cosmology around it. The cold spot has never quite reached that level. It keeps approaching the door, knocking loudly, and then refusing to provide identification. Polarization offered one possible way to learn more. Remember that CMB temperature fluctuations produced at the surface of last scattering are statistically related to polarization patterns generated by scattering in the early universe. If the cold spot is simply an unusually large primordial Gaussian fluctuation, certain correlated polarization features should be expected around it. If, instead, some secondary process altered the temperature of CMB photons long after they left the early universe, the same polarization relationship might not appear. That makes polarization useful as a partly independent test. Researchers recognized this possibility before Planck's final polarization maps became available. There was considerable hope that better polarization measurements might help distinguish between an ordinary primordial fluctuation and some additional physical mechanism. WMAP's polarization data were too noisy on the relevant scales to provide a strong answer. Planck improved the situation dramatically. Its final large-scale polarization analysis was released as part of the mission's legacy results. The outcome was not the clean resolution anyone might have preferred. Planck did not find statistically significant polarization counterparts to the large-scale temperature anomalies. That included the cold spot. At first, you might think this means the cold spot cannot be primordial. It is not that simple. The polarization measurements and the expected signals are subtle enough that the absence of a strong anomaly does not decisively reject the standard explanation, nor does it prove a secondary origin. The Planck team concluded that the polarization data neither confirmed the temperature anomalies as new physics nor eliminated their possible importance. This is almost perfectly designed to frustrate anyone hoping for a dramatic ending. The temperature feature is there. The polarization data do not reproduce an equally obvious anomaly, but the absence of that signal is not strong enough to tell us exactly why. The final Planck analyses therefore left the basic situation remarkably similar to where it had been before. The standard cosmological model remains highly successful. The CMB temperature field is broadly compatible with Gaussian statistics. No unambiguous detection of cosmological non-Gaussianity emerged from the final polarization analysis. Yet the cold spot remains one of the conspicuous large-scale temperature features that sits awkwardly within an otherwise excellent fit. This is why describing it as unexplained requires a little care. Scientists can explain how something like it might occur. A sufficiently rare primordial fluctuation could create one. There is nothing mathematically forbidden about that. What they cannot do is point to one explanation and say with confidence that this is definitely what happened. That distinction matters. Unexplained does not mean physics has no ideas. It means the available observations have not selected one idea strongly enough. The ordinary explanation is statistical chance. The cold spot may simply be an extreme member of the same population of fluctuations responsible for every other hot and cold region in the CMB. If so, there is nothing additional to discover about its origin. We found the weirdest patch on a very large map. Naturally, the weirdest patch looks weird. The extraordinary possibilities begin only if that explanation becomes too improbable. Then something else may have contributed. Perhaps the photons changed energy while passing through a large structure between the CMB and us. Perhaps the pattern was generated by unusual early universe physics. Perhaps there is some phenomenon associated with inflation that is not captured by the simplest models. More speculative suggestions have involved topological defects known as cosmic textures. Others have gone much farther. The possibility that our observable universe might have interacted with another region during an inflationary multiverse has occasionally been discussed in connection with unusual CMB structures. That is where the famous claims about another universe enter the story. It is worth keeping them firmly at the speculative end of the shelf. The existence of a cold spot does not demonstrate a multiverse. No observation of the region has established that interpretation. A strange microwave patch and proof of another universe are separated by a very large amount of evidence that nobody currently possesses. Still, scientists investigate exotic explanations because unusual observations are exactly where new physics would be expected to reveal itself if new physics is present. The sensible approach is not to believe the strangest possibility, it is to compare possibilities. What does each explanation predict? Does it reproduce the cold spot's angular size, its temperature, its radial profile, its frequency independence, its polarization behavior? Does it require an object or phenomenon that should produce another observable signal? Can that signal be searched for? A good explanation should do more than say that something strange could happen. It should survive measurements. This requirement caused problems for many proposed solutions. Take the simplest primordial interpretation. A Gaussian fluctuation requires no new physics and is therefore attractive. It automatically has the correct basic frequency behavior because it is part of the CMB itself. The difficulty is its rarity under some statistical measures. Then consider an unknown foreground. Foregrounds can produce large features, but the cold spot appears consistently across frequencies in a way expected for the CMB, and Planck's broad frequency coverage made ordinary foreground explanations increasingly difficult. Instrumental error became similarly unattractive once Planck reproduced a feature previously seen by WMAP. A secondary cosmological effect therefore offered an appealing middle ground. No exotic early universe physics would be required. Instead, something along the line of sight could change the energy of CMB photons after they had left the surface of last scattering. General relativity already provides mechanisms for this. Photons moving into and out of gravitational potentials can gain and lose energy. If the universe were completely static, much of the effect would cancel. But the universe evolves while the photon is travelling. Dark energy changes how large gravitational potentials develop at relatively recent cosmic times. As a result, a photon can emerge with a slightly different energy from the one it had before entering a large structure. This is associated with what is known as the integrated Sachs-Wolf effect. There are also nonlinear versions of these gravitational effects, often discussed under the Rees-Siyama effect. The details can become technical very quickly, but the basic concept is friendly enough. Imagine a ball rolling down into a valley and then climbing out the other side. If the valley remains exactly the same while the ball crosses it, the energy gained on the way down can be matched by the energy lost climbing out. Now imagine the valley becoming shallower during the crossing. The accounting changes. CMB photons moving through evolving gravitational structures can experience an analogous effect. A large underdense region, a cosmic void, represents one possible structure capable of leaving a small temperature imprint. If an exceptionally large void lay between us and the cold spot, perhaps ancient CMB photons passed through it and lost enough energy to appear colder when they finally arrived here. This explanation had several advantages. Cosmic voids definitely exist. The integrated Sachs-Wolf effect definitely exists in standard cosmology. No new particles were required, no collisions between universes, no exotic defects left over from phase transitions, just gravity, cosmic expansion, and a very large empty region. That made it an obvious hypothesis to test. If the cold spot were caused mainly by something in the foreground, astronomers should be able to search the direction of Eridanus and examine the distribution of galaxies between us and the microwave background. A void contains less matter than average. Fewer galaxies should be found across at least part of the relevant distance range. Modern galaxy surveys are designed to map exactly this sort of large-scale structure. So astronomers looked. What they found was immediately intriguing. The line of sight toward the cold spot does contain an unusually underdense region. It is commonly called the Eridanus supervoid. Depending on how it is mapped and defined, it appears to extend across an enormous volume and may consist of several connected underdense structures rather than one perfectly simple spherical whole. For anyone hoping for a conventional explanation, this sounded promising. There was an anomalously cold patch in the microwave background. Astronomers searched the same direction. They found an enormous deficit of galaxies. Known general relativity provides a mechanism linking evolving cosmic voids to CMB temperature shifts. For a brief moment, the mystery appeared to be moving toward a rather tidy solution. The problem was that discovering a supervoid and explaining the cold spot are not the same calculation. Researchers now had to determine the void's distance, width, depth, density profile, and geometry. Then they had to calculate how strongly such a structure should alter the microwave radiation passing through it. That calculation begins with a strange fact about empty space. It is not really empty. When astronomers describe a cosmic void, they do not mean a completely vacant region containing no matter at all. A void is simply a part of the universe containing much less matter than the cosmic average. There may still be galaxies inside it. There may still be gas, dark matter, and isolated groups of stars. There is just considerably less of everything than you would expect to find in a typical region of the same size. And on the larger scales, these voids are everywhere. Galaxies are not distributed randomly through space like grains of salt scattered across a table. They form an enormous network called the cosmic web. Dense clusters of galaxies sit at intersections. Long filaments connect them. Broad sheets of matter stretch between those filaments. Between all of this structure lie enormous underdense regions, voids. Some are tens of millions of light years across, others are much larger. The largest structures are sometimes called supervoids, although there is no single sharp boundary where a respectable ordinary void suddenly earns the promotion. These structures developed because the early universe contained tiny differences in density. Regions containing slightly more matter attracted additional matter through gravity. Regions containing slightly less matter gradually lost material to their denser surroundings. Over billions of years, the contrast increased. Dense places became denser. Empty places became emptier. The result is the cosmic web we observe today. So there is nothing unusual about finding a void. Finding an exceptionally large one precisely in the direction of one of the strangest temperature features in the cosmic microwave background is rather more interesting. That possibility had actually been discussed before astronomers had a detailed three-dimensional map of the cold spot's foreground. The reason came from a subtle effect predicted by general relativity. A photon travelling through the universe does not simply ignore large concentrations or deficits of matter. Those structures produce gravitational potentials, and photons can change energy while passing through them. Imagine a CMB photon approaching a massive galaxy cluster. As it falls into the cluster's gravitational potential, it gains energy. As it climbs back out, it loses energy. If the gravitational potential remains exactly unchanged during the crossing, the two effects nearly cancel. the photon leaves with roughly the energy it had before entering. A large cosmic void creates the opposite type of potential structure, but the same basic accounting applies. The complication is that our universe is not static, it expands. At relatively recent cosmic times, that expansion has been accelerating, which we attribute to dark energy. Because the universe changes while the photon is crossing a gravitational structure, the potential itself can change during the journey. The photon may therefore leave with slightly more or slightly less energy than it would have had in an unchanging universe. This is the integrated Sachs-Wolfe effect, usually shortened to ISW. The name comes from Rainer Sachs and Arthur Wolfe, who described the underlying effect in the 1960s. It is not responsible for most of the temperature structure in the CMB. Most of the pattern was already imprinted when the radiation began travelling freely. The ISW effect adds a much smaller secondary signal later. A photon crossing a very large evolving overdensity can emerge slightly hotter. A photon crossing a large evolving underdensity can emerge slightly colder. That immediately sounds useful. We have a cold patch. We have a mechanism capable of making CMB photons colder. Perhaps all we need is an enormous void in front of it. This idea became especially attractive because the cold spot is much larger on the sky than an ordinary galaxy cluster or ordinary cosmic void. Any foreground structure capable of affecting such a broad region would itself need to be enormous. Astronomers therefore began searching the distribution of galaxies toward Eridanus. One of the major investigations used galaxies identified in infrared observations from WISN 2 mass, combined with optical information from pan-stars. Instead of looking only at a flat picture of how many galaxies appeared in each direction, researchers tried to estimate their distances using redshifts. Redshift is useful because cosmic expansion stretches light from distant galaxies. In general, larger cosmological redshift means greater distance, although converting the two precisely requires a cosmological model, and peculiar motions can add complications nearby. By dividing galaxies into redshift ranges, astronomers can build something like a rough three-dimensional map. That map revealed a substantial shortage of galaxies along the cold spot line of sight. The deepest part appeared at a redshift around 0.15 to 0.25. The original analysis was consistent with an underdense structure having a characteristic radius of roughly 220 megaparsecs divided by the Hubble parameter convention, commonly written as h, with significant uncertainty in that estimate. Translated into less technical language, the structure was enormous. Depending on the exact definition and geometry being used, its scale could correspond to hundreds of millions of light years. The average matter density appeared to be lower than normal by roughly 10 to 20%, with some estimates placing the central underdensity deeper. This became known as the Eridanus supervoid. At first glance, the alignment seemed remarkable. The CMB contains a rare, large cold region. The late-time universe contains a rare, large underdense region. Both appear in approximately the same direction. There was even a known physical mechanism that could connect them. For anyone who prefers explanations involving established gravity rather than unknown physics from the first instant of creation, this was encouraging. The cold spot might not be a primordial anomaly at all. It might simply be an ordinary patch of the early CMB whose photons happen to pass through an extraordinary foreground structure. That would mean the apparent scar in the oldest light was actually much younger than it looked. The photons themselves would still be almost as old as the observable universe. Their unusual temperature, however, would have been modified comparatively recently. The idea became more interesting because voids can produce a temperature pattern that superficially resembles part of what we see around the cold spot. A large central underdensity can generate a cold imprint, and depending on the void's density profile and surrounding matter, the temperature pattern may include warmer structure around the outside. Remember that one of the notable characteristics of the cold spot is its surrounding hot ring. A model that can naturally create both a cool center and surrounding structure sounds promising. Unfortunately, being able to draw the correct general shape is not enough. The numbers have to work. The first difficulty concerns how weak the integrated Sachs-Wolf effect normally is. Gravity certainly affects the CMB photons. The question is how much. Under the standard lambda-CDM cosmological model, even very large voids produce relatively small ISW temperature shifts. The Eridanus structure is large, but it is not empty enough to remove enormous amounts of matter from the line of sight. A density deficit of perhaps 20 or 25% spread across a vast region is significant for large-scale structure studies. It is not the same thing as carving a completely empty spherical hole through the universe. When researchers modelled the expected ISW signal from the observed supervoid, they generally obtained a temperature decrement much smaller than the full cold spot. Depending on the void model, geometry and data used to describe the underdensity, predictions often land in the range of a few tens of microkelvin. The cold spot's central temperature depression can be well over 100 microkelvin relative to the mean once particular filtering and profiles are considered. Those values should not be compared too casually, because different papers define the profiles and smoothing in different ways. The overall mismatch, however, is the important part. Under standard cosmology, the observed Eridanus supervoid does not appear capable of producing the entire cold spot by itself. Later analyses have commonly estimated that its normal ISW contribution might account for only around 10 to 20% of the observed depression. That is not nothing. If a void contributes 20% of an anomaly, it is still part of the story. It simply is not the whole story. For the supervoid explanation to solve everything, the gravitational effect would need to be considerably stronger than the standard model predicts, or the structure would need to be much more extreme than observations indicate. Researchers explored both possibilities. Perhaps the shape of the void had been oversimplified. Early calculations often represented supervoids as roughly spherical objects because spherical models are mathematically manageable. Real cosmic structures are rarely so cooperative. They twist, they merge, they contain smaller voids, sheets, filaments and clusters. A structure that looks broad on the sky might extend much farther along our line of sight than it does sideways. This matters because an elongated supervoid could influence CMB photons over a greater distance. More detailed maps did suggest that the Eridanus underdensity may be elongated toward and away from us. One reconstruction found a transverse characteristic scale of roughly 200 megaparsecs divided by h, while its line of sight extent could reach several hundred megaparsecs divided by h. Rather than one neat spherical cavity, the structure may be better thought of as a chain or complex of connected underdense regions. That is much closer to what the cosmic web actually looks like. Unfortunately, giving the void a longer shape still did not provide enough cooling under standard lambda-CDM calculations. Models of an elongated Eridanus supervoid have produced an ISW signal of roughly -40 microkelvin in some cases. That is larger than the simplest spherical estimates. It remains too small to reproduce the complete cold spot temperature pattern. Researchers also examined the nonlinear gravitational contribution known as the Rees-Sciamma effect. The integrated Sachs-Wolf effect is usually calculated from the large-scale evolution of gravitational potentials in the linear regime, where density fluctuations have not become too extreme. The Rees-Sciamma effect describes additional changes caused by nonlinear evolution. A large void is changing as matter moves around it and the surrounding universe develops. Perhaps those nonlinear changes could give CMB photons an extra temperature shift. Some early proposals suggested that the Rees-Sciamma contribution from a sufficiently enormous void might be surprisingly large. That raised hopes that the missing temperature decrement could be found there. More detailed calculations were less encouraging. Analyses using both perturbative methods and exact relativistic models found that the nonlinear Rees-Sciamma contribution for a void like the one observed toward Eridanus is much smaller than would be required. The ordinary linear ISW contribution remains dominant on these large scales. adding nonlinear evolution does not conveniently multiply the effect until the cold spot is explained. The universe declined to balance the spreadsheet. Another approach was to ask the reverse question. Instead of starting with the observed void and calculating the CMB temperature shift, researchers could start with the cold spot and calculate what kind of void would be required to produce it. That gives a rather uncomfortable answer. A void capable of creating the entire anomaly through standard gravitational effects would have to be extraordinarily large, extraordinarily deep, or both. It would be far more extreme than the already impressive structure actually observed. Within the standard lambda-c dm model, forming such a structure would itself be exceptionally improbable. So the explanation would simply replace one anomaly with another. You begin with an unusually cold CMB feature. You explain it by proposing an unbelievably extreme supervoid. Now you must explain why that unbelievably extreme supervoid exists. This is not necessarily progress. There is another observational complication. If the cold spot were caused entirely by a single giant foreground void, astronomers should find a galaxy distribution matching the required simple structure. Spectroscopic surveys can test this more precisely than photometric distance estimates. Photometric redshifts estimate galaxy distances from their colours and brightnesses. They're extremely useful when surveying huge numbers of galaxies, but their distance estimates are relatively broad. Spectroscopic redshifts use specific features in a galaxy's spectrum and usually provide much better precision. A dedicated redshift survey therefore examined thousands of galaxies toward the central part of the cold spot. It found under dense regions at several redshifts there were voids around redshifts of approximately 0.14, 0.26 and 0.30, but these were interspersed with smaller overdense regions. Instead of one enormous clean cavity stretching through space, the line of sight contained a more complicated sequence of structures. This is exactly what you might expect from the cosmic web. It is less useful if you were hoping for one simple object capable of producing the entire microwave anomaly. The survey compared the cold spot direction with a control field. Interestingly, the control line of sight showed a somewhat similar pattern of galaxy underdensities and overdensities, yet it did not contain an equivalent CMB cold spot. That provided another reason to doubt that ordinary foreground void structure was sufficient. Later observations improved the mapping again. The Dark Energy Survey, or DES, provided detailed information about galaxies over a large area of the southern sky. It also allowed researchers to use weak gravitational lensing. Gravitational lensing occurs because matter bends the path of light. The distortions produced by large-scale structure are tiny, but when astronomers measure the shapes of enormous numbers of distant galaxies statistically, they can reconstruct aspects of the mass distribution between those galaxies and us. That matters because counting galaxies is only an indirect way of tracing matter. Most matter is dark matter. Weak lensing offers a way to investigate total mass more directly. DES data confirmed that the Eridanus supervoid is not merely a strange result caused by one particular galaxy catalogue. A significant underdensity really is present toward the cold spot. In reconstructed dark matter maps, it stands out as an unusually prominent low-density structure, so the supervoid did not disappear as observations improved. Much like the cold spot itself, it survived. And that leaves us with a peculiar coincidence. There really is a large CMB anomaly. There really is an unusually large foreground underdensity roughly aligned with it. But according to standard calculations, the foreground underdensity is not strong enough to make the entire CMB anomaly. Two unusual things appear in nearly the same direction without a fully convincing explanation of their relationship. Some researchers therefore argue that the alignment itself should not be dismissed. Even if the Eridanus supervoid explains only part of the cold spot, perhaps it combines with an unusually cold primordial fluctuation already present in the CMB. Imagine that the original microwave sky happened to contain a moderately rare cold region. Then the photons from that region travelled through an unusually large void. The void cooled them slightly more through the ISW effect. Neither ingredient alone would have to be extreme enough to explain the full anomaly. Together, they could produce something closer to the observed cold spot. This kind of combined explanation is less dramatic than a completely new physical phenomenon. It also becomes statistically complicated. You now need to ask how likely it is for an unusually cold primordial fluctuation and an unusually large foreground supervoid to align closely enough to reinforce each other. That alignment may itself be unusual. Estimating exactly how unusual depends on how the structures are defined. The supervoid's angular center does not correspond perfectly to every definition of the CMB Cold Spot center. Its geometry is complex. Different surveys reconstruct somewhat different boundaries. The cold spot itself changes appearance depending on the angular filter used. The phrase, "they line up," is therefore true in a broad sense, without meaning that two perfect circles have been drawn on the universe and placed exactly on top of each other. There is also a separate issue that keeps the supervoid discussion alive. Measurements of the ISW signal from other large voids have sometimes appeared stronger than lambda CDM predicts. Researchers can identify collections of supervoids in galaxy surveys, stack CMB maps at their positions, and look for an average cold signal. Some studies have reported temperature imprints several times stronger than expected. Other analyses have found results consistent with the standard prediction. This has produced its own long-running debate involving how voids are selected, how their sizes are defined, how filters are chosen, and how statistical uncertainties are estimated. If supervoids genuinely imprint stronger CMB signals than standard calculations predict, then Eridanus becomes more interesting again. An enhanced ISW effect could potentially account for a larger fraction of the cold spot, but there is a major difference between saying observations hint at an unexpectedly strong average signal and demonstrating a physical mechanism capable of producing it. At present, standard lambda CDM does not naturally give the Eridanus supervoid enough influence. One would need either an underestimated astrophysical effect, unusual properties of dark energy or gravity, a statistical coincidence, or some combination of factors. Recent studies have continued examining foreground explanations rather than treating the problem as closed. There have even been proposals that nearby galaxies and local extragalactic environments in the Eridanus direction might contribute additional microwave foreground structure. These ideas are different from the classic supervoid explanation, and they remain under investigation. What has become increasingly difficult to defend is the simple statement that a single conventional giant void cleanly explains the entire cold spot. The void exists. It probably affects CMB photons passing through it. The expected effect has the correct sign. It may account for a fraction of what we observe. It just does not appear to account for enough. That distinction is important because the phrase supervoid explanation failed can also be too strong. Nothing requires the cold spot to have only one cause. The observed temperature in any direction can contain several contributions. There is the primordial CMB fluctuation. There are gravitational effects accumulated during the photon's journey. There can be gravitational lensing. There are astrophysical foregrounds. There is measurement noise. There may be smaller secondary effects. What we call the cold spot is the final combination arriving at our instruments. Perhaps the Eridanus supervoid contributes -20 or -40 microkelvin to a primordial region that was already cold. Perhaps part of its unusual warm ring is influenced by foreground structure. Perhaps the alignment is accidental, and the supervoid has almost nothing to do with why the original CMB patch is statistically unusual. The available measurements do not yet give one clean answer. The strongest conclusion is more modest. An enormous underdensity lies in roughly the correct direction, but within the standard cosmological model, its expected gravitational imprint is too weak to reproduce the full anomaly. That pushes the investigation backward again. If the Eridanus supervoid cannot produce enough cooling to explain the entire cold spot, then at least part of the answer may have to come from much earlier in cosmic history. Much earlier. Not a few billion years ago, when galaxies and voids were developing across the universe. not 380,000 years after the Big Bang, when the cosmic microwave background finally began travelling freely. We have to consider conditions so early that ordinary matter had not yet taken on anything resembling its familiar form. This brings us back to inflation. Inflation is the name given to a proposed period of extremely rapid expansion during the earliest moments of the universe. The basic idea was introduced to solve several problems that arise when we compare the simple hot Big Bang model with what we actually observe. One of those problems is the remarkable uniformity of the cosmic microwave background. Look in one direction and measure its temperature, then turn almost completely around and measure it again. The temperatures are almost identical. That is surprising because, in a simple universe without inflation, some of those distant regions would not appear to have had enough time to exchange information with each other before the CMB was released. They should not have been able to settle into nearly the same temperature. Inflation changes that story. Before the rapid expansion, regions that are now enormously far apart could have been much closer together and able to interact. Inflation then stretched space at an extraordinary rate, carrying those regions away from each other while preserving their similar initial conditions. Inflation also offers an explanation for another important feature of the universe. The tiny density fluctuations that later became galaxies may have begun as quantum fluctuations on microscopic scales. Inflation stretched them enormously. Once expanded to cosmic sizes, those fluctuations became the initial irregularities from which larger structures eventually grew. That general picture fits the statistical properties of the CMB remarkably well. There is, however, a problem with the word inflation. It sounds like one theory. It is really a family of theories. Physicists have developed many different inflationary models involving different fields, different potential energies, different durations, and different mechanisms for starting and stopping the rapid expansion. Some versions end everywhere, others do not. And once inflation refuses to end everywhere at the same time, things become considerably more complicated. In some models, inflation is eternal. That does not necessarily mean our own observable universe continues inflating today. It means the larger inflating environment may continue expanding even while inflation ends in individual regions. Imagine an enormous volume of rapidly expanding space. In one location, the field responsible for inflation changes state. Inflation ends there. That region can begin evolving into a universe containing matter, radiation, galaxies, and eventually observers who become concerned about unusual patches in microwave maps. Elsewhere, inflation continues. Then it ends in another region, and another. Each region is often described as a bubble universe. The terminology can be misleading. These are not soap bubbles floating through ordinary three-dimensional space. There is no cosmic bath filled with spherical universes bumping gently against one another. A bubble is a region where the physical state associated with inflation has changed. Its interior can expand and evolve in its own way while the surrounding false vacuum region continues inflating. The mathematics behind this involves quantum field theory, general relativity, and the behavior of vacuum states. Fortunately, we can leave most of that mathematics exactly where it is. The useful idea is simple enough. If multiple bubble regions can form, then bubbles can sometimes collide. And if our observable universe developed inside one bubble, a collision with another bubble could, under certain models, affect part of what later became our observable sky. That is the connection to the cold spot. The collision would not have happened last week. It would not have involved two fully developed universes containing galaxies crashing together like cars in an intersection. It would have happened extraordinarily early, when the regions involved were still governed by inflationary fields and extreme high-energy physics. The disturbance created by that interaction could then have evolved along with our universe. Billions of years later, part of its signature might appear in the cosmic microwave background. This is an attractive idea for one very specific reason. The CMB is exactly where we would look for evidence of an event that affected the early universe on a very large scale. The microwave background preserves information about primordial density and gravitational fluctuations. If something produced an unusually broad disturbance before recombination, the photons released later could carry an imprint of it. Some bubble collision models predict a roughly disc-shaped feature on the CMB sky. Inside the affected region, the temperature may vary systematically. The centre can appear hotter or colder, depending on the details of the collision and the underlying fields. The edge of the region may also contain a characteristic transition. That immediately makes the idea sound relevant. The cold spot is broad. It has a roughly localized shape, is unusually cold. Perhaps, then, we are looking at the remains of a collision involving another bubble universe. This is the point where popular descriptions often become much more confident than the scientific evidence allows. The cold spot is not accepted evidence of another universe. No bubble collision has been detected. No observation has established that another universe touched ours. What exists is a theoretical possibility. Certain models of eternal inflation permit bubble collisions. Some of those collisions could leave CMB signatures. Researchers have therefore searched real CMB maps for those signatures. That is very different from discovering one. The distinction matters because almost any unusual circular feature in the CMB can look suggestive if the theoretical model is flexible enough. A useful scientific test needs a more precise prediction. Researchers therefore asked what a bubble collision should actually do. A collision can perturb the field that drove inflation inside our bubble. That perturbation changes the local expansion history. Different parts of the affected region may undergo slightly different amounts of inflation. Those differences can become curvature or density perturbations. Eventually they influence the temperature of the CMB. Depending on the model, the effect can produce a broad circular region whose temperature changes across its radius. A particularly important feature is that causality restricts where the collision can have an influence. The disturbance does not simply alter the entire CMB sky in an arbitrary pattern. There can be a boundary separating the region affected by the collision from the unaffected region. Projected onto our sky, that boundary may appear approximately circular. This gave scientists something concrete to search for, not just cold spots. Circular localized temperature patterns with profiles resembling the predictions of bubble collision calculations. Several researchers began developing systematic searches. This was important because of the statistical problem we encountered earlier. If you notice the cold spot first and then invent an exotic model capable of producing something vaguely similar, it is very easy to overestimate how impressive the agreement is. A better approach is to define the predicted signal, search the whole sky using the same rules everywhere, and compare the evidence for a universe with bubble collisions against the ordinary lambda-c DM model. Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris carried out one of the first major observational searches of this kind using 7 years of WMAP data. Their method looked for candidate bubble collision signatures without beginning from the assumption that the cold spot itself must be one. That is a much stronger test. If eternal inflation had left several detectable collision scars around the sky, the algorithm should have a chance of finding them. The researchers first identified potentially interesting features. Then they examined whether the candidates contained the kind of circular boundaries expected in collision models. Finally, they used Bayesian statistical methods to compare models with and without bubble collisions. Several candidate features appeared. That was not surprising. The CMB contains many fluctuations, and some random structures will resemble almost any template to some degree. The important result came from the model comparison. The WMAP data did not provide sufficient evidence to justify adding bubble collisions to the standard cosmological model. The researchers were able to place limits on how many detectable bubble collisions could exist across the sky. Their analysis constrained the expected number rather than finding a convincing example. That is not the result you would expect if the cold spot had already provided clear evidence of another universe. The situation became even more interesting because the predicted collision signatures are not identical to the cold spot's famous wavelet profile. A bubble collision can make a broad hot or cold disk, but the exact radial shape depends on the collision physics. The cold spot, meanwhile, has a cold central region combined with surrounding structure, including its warmer ring. Matching one feature is easy. Matching the entire temperature profile, polarization pattern, angular size, and statistical behavior is much more difficult. There is also a geometrical issue. If our bubble experienced a collision, the observable trace depends heavily on where that event occurred relative to the portion of the bubble that became our observable universe. Many collisions would leave no signal we could see. Some would affect an enormous fraction of the sky. Others could create smaller disks. The probability of observing a particular size depends on the underlying model of eternal inflation. That means the theory does not simply say there should be one cold circle about 10 degrees wide. It produces a distribution of possible signals determined by quantities we do not yet know. Those quantities include the expansion rate of the false vacuum outside our bubble, the rate at which bubbles nucleate, the properties of the inflationary potential, the structure of the bubble walls, and what happened to the fields during the collision. There are a great many adjustable pieces. This can make the model flexible enough to produce interesting effects while also making it difficult to test decisively. Physicists have therefore used numerical relativity to simulate bubble collisions more carefully. Instead of treating the collision as a simple painted disk on the microwave sky, they solve equations describing the evolving spacetime and scalar fields. They can follow how a disturbance created by the collision develops inside the bubble, survives inflation, and later becomes a curvature perturbation. That perturbation can then be translated into predicted temperature and polarization patterns in the CMB. These calculations have shown that collisions can, at least in principle, leave observable signatures. They have also shown that the exact signal depends strongly on the physical model. A collision does not automatically create a cold spot. Some collisions produce hot regions, some create temperature gradients, some produce signals too weak to detect, some affect angular scales larger or smaller than the cold spot. Some may be hidden by ordinary primordial fluctuations. The general possibility survives. The specific identification remains unsupported. Polarization again becomes useful. A genuine primordial disturbance from a bubble collision should influence not only temperature, but also the way matter and radiation behaved before the CMB was released. That can create a correlated polarization pattern. Different collision models predict different details, but in general, temperature and polarization together provide a better test than temperature alone. This was one reason Planck polarization data were so eagerly anticipated. A temperature map can contain an accidental cold disk. Finding the associated polarization expected from a physical collision would be much harder to dismiss. Planck did not provide such decisive evidence. Its polarization observations did not reveal a statistically significant counterpart that transformed the cold spot into a confirmed primordial anomaly. More broadly, Planck's measurements continue to fit the standard lambda CDM model extremely well. There was no accepted bubble collision detection hiding in the final data. This does not prove that eternal inflation is wrong. It does not even prove that bubble collisions never occurred. A collision could have been too weak. It could have happened outside our observable region. Its signal could lie below cosmic variance. The parameters of the inflationary model could make detectable collisions extremely rare. But those possibilities also mean the cold spot cannot be used as straightforward evidence for the multiverse. There is a useful difference between a theory being capable of producing something and a theory being supported by that thing. A thunderstorm is capable of producing a power outage. If your house loses electricity, you cannot conclude that a thunderstorm caused it without checking whether a storm actually occurred. Perhaps a cable failed. Perhaps a transformer broke. Perhaps someone attempting home improvement made an ambitious decision involving the fuse box. Bubble collisions occupy a similar position in the cold spot discussion. They could produce large CMB features. The existence of a large CMB feature does not tell us that a bubble collision produced it. There is another subtlety hiding inside the phrase, another universe. In many eternal inflation models, another bubble is not necessarily a separate universe in the everyday science fiction sense. It may be another region of a larger inflating space-time. Depending on the underlying theory, that region could have different low-energy physics. It might settle into a different vacuum state. Particle masses or forces could differ, or it could be broadly similar to ours. There is no single universally accepted multiverse model that tells us exactly what lives inside every possible bubble. So even if a collision signature were detected, scientists would still have a long way to go before describing the other side. We would not immediately know whether it contained galaxies. We would not know whether it produced stars. We certainly would not know whether someone over there had also noticed a suspicious microwave patch and blamed us. What would make a genuine collision detection extraordinary is more fundamental. It would provide evidence that the region we call our universe is embedded in a larger physical structure. It could turn ideas associated with eternal inflation from largely theoretical constructions into something at least partly observable. That would be one of the most significant discoveries in cosmology. Because the consequences would be so large, the evidence has to be correspondingly strong. One unusual cold feature is not enough. This is especially true because there are less exotic ways to create unusual primordial structures. Inflation itself can behave irregularly without requiring another bubble to collide with ours. The field driving inflation might encounter a feature in its potential. A second field might briefly become important. A phase transition could occur. Rare quantum fluctuations could produce localized disturbances. Each of these possibilities can alter the primordial density field and potentially leave features in the CMB. Researchers have developed models of localized primordial bubbles or density perturbations that can produce cold spot-like structures without invoking a collision between universes. One such proposal imagines an unusually large spherical underdensity or overdensity generated during inflation. If positioned near the surface of last scattering, it could produce a broad CMB feature through gravitational effects. The result might resemble the cold spot while remaining entirely inside our own inflationary history. That is still exotic compared with an ordinary Gaussian fluctuation. It is simply less exotic than another bubble universe arriving from outside. Then there are cosmic textures. These are hypothetical defects that could have formed during symmetry-breaking phase transitions in the early universe. They provide another mechanism capable of creating isolated hot or cold features. Textures became one of the better-known exotic cold spot proposals because the predicted temperature profile can resemble the observed anomaly reasonably well under some assumptions. We will encounter that idea more closely as the possible explanations continue to narrow. The important point here is that a bubble collision must compete with several alternatives. It is not another universe or nothing. It is another universe or an ordinary random fluctuation, or an unusually large primordial perturbation, or a cosmic defect, or a partial foreground contribution combined with primordial coldness, or some other effect that has not been isolated. Every explanation has costs. The Gaussian fluctuation explanation has the cost of rarity. The supervoid explanation has the cost of an insufficient temperature effect. A bubble collision has the cost of invoking a highly model-dependent physical scenario for which there is no independent observational evidence. A cosmic texture requires new high-energy physics. Other inflationary features introduce additional parameters. Scientists compare these costs through likelihoods, Bayesian evidence, predicted observables, and consistency with everything else we know about the universe. The most exciting explanation does not receive extra points for being exciting. Usually it receives extra questions. This is why systematic bubble collision searches matter more than visual resemblance. The WMAP analyses did not find evidence requiring collisions. Forecasts made for Planck suggested that its temperature and polarization data could significantly improve constraints, especially if a sufficiently strong signal existed, yet no accepted collision signature emerged. As CMB measurements became more precise, the simplest cosmological model continued to survive. The cold spot survived too, but without acquiring the additional evidence needed to identify it with eternal inflation. That leaves the possibility in an unusual position. The physics is speculative, but not meaningless. The predictions can be calculated. Search algorithms can be constructed. Candidate signals can be tested. Constraints can be placed. This is not the same as inventing an untestable story around a blue patch on a map. At the same time, no result currently requires the bubble universe interpretation. That distinction is often lost when the cold spot appears in popular discussions. The phrase, "possible evidence of a parallel universe," is technically easier to print than "an anomaly has motivated searches for model-dependent signatures predicted by some versions of false, vacuum, eternal inflation," none of which has been detected convincingly. The second version is considerably less likely to become a thumbnail. It is also much closer to the scientific situation. There is another reason physicists remain interested in these searches even without a detection. The cosmic microwave background may offer one of the very few possible observational routes to physics occurring near the inflationary era. Particle accelerators can probe enormous energies by human standards. The early universe operated at scales potentially far beyond anything we can reproduce. If inflation occurred, the CMB carries indirect information from that period. An unusual localized feature could contain information that is averaged away in the ordinary power spectrum. Most cosmological analyses treat the CMB statistically. They ask how much variation exists at different angular scales across the whole sky. This is incredibly powerful, but it can hide rare localized events. A bubble collision would not necessarily change the average statistics dramatically. It might leave one or a few particular regions. That means searching for individual structures remains scientifically worthwhile, even when the overall CMB agrees beautifully with lambda CDM. The cold spot is exactly the kind of feature that encourages such searches. It is large enough to attract attention. It persisted from WMAP to Planck. Its simple foreground explanation struggles, and its statistical status remains uncertain enough that nobody can confidently discard it. None of those facts point specifically to another universe. Together they keep primordial possibilities on the table. Suppose, purely for illustration, that the cold spot did come from a bubble collision. The event would have happened before any star existed. The disturbance would have been stretched and processed during the subsequent expansion of our universe. For hundreds of thousands of years, matter and radiation would have evolved within that altered region. When the universe became transparent, photons leaving it would carry a slightly different temperature pattern. Those photons would then spend more than 13 billion years crossing expanding space. Some would pass through the Eridanus supervoid, adding another small gravitational modification along the way. Eventually they would reach Earth. WMAP would measure them. Scientists would notice an unusual wavelet coefficient. Planck would confirm the temperature feature, and only then would we begin asking whether the pattern had anything to do with an event from an era almost unimaginably earlier. That chain of reasoning is possible. It is not demonstrated. To move from possible to persuasive, scientists would need additional signatures. A characteristic polarization pattern would help. A sharp causal boundary predicted by a particular collision model would help. Several spots sharing the expected statistical distribution would be more convincing than one isolated anomaly. Independent evidence favouring eternal inflation would make the interpretation less costly. None of those has appeared at a level that establishes the case, so the bubble collision idea remains where many fascinating cosmological ideas spend much of their lives. Mathematically serious, observationally testable in principle, heavily constrained and not confirmed. That still leaves a useful question. If a collision with another inflationary bubble is not required, could some other relic from high-energy physics create a localized cold spot without needing an entire neighboring universe? That possibility begins with something called a cosmic texture. The name is slightly misleading. A cosmic texture is not a material floating through space, and it has nothing to do with the texture of matter in the ordinary sense. It is a hypothetical defect in a field that could have formed when the very early universe cooled and underwent a major change in its physical state. We are familiar with phase transitions in everyday life. Cool water below its freezing point and it becomes ice. Heat a magnet sufficiently and it can lose its magnetization. In both cases, the underlying material changes from one organized state to another. The early universe is thought to have passed through far more extreme versions of this process. At very high temperatures, some of the forces and fields that appear different today may have behaved as parts of more symmetric physical systems. As the universe expanded and cooled, those symmetries could have broken. A useful comparison is a crowd of people who are all asked to choose a direction at the same moment without being able to communicate with people far away. One group points north, another points east, another chooses southwest. Most neighbouring groups eventually settle into compatible choices, but in some places the different orientations cannot be smoothly reconciled. A defect remains. The exact type of defect depends on the mathematical structure of the field undergoing the transition. Some theories produce domain walls, others produce monopoles, some create cosmic strings, which would be extremely thin concentrations of energy, stretching across enormous distances, and certain symmetry-breaking patterns can create textures. Unlike a cosmic string, a texture is not a permanent line-like object. It is more like a large unstable knot in the configuration of a field. As the universe evolves, that knot can collapse. The energy becomes increasingly concentrated. Eventually the field can unwind, releasing the configuration and allowing it to settle into a simpler state. None of this would involve a visible knot floating between galaxies. The relevant field would be something associated with physics at energies far beyond those available in ordinary matter. But the changing gravitational field of a collapsing texture could affect photons passing nearby. That is where the cosmic microwave background becomes useful. Imagine a texture beginning to collapse while CMB photons are moving through the region. As the photons enter the evolving gravitational potential, their energies change. Because the texture itself is changing during the crossing, the photons do not necessarily recover exactly the same energy when they leave. Depending on whether the texture is collapsing or unwinding relative to the photon's journey, the result can appear as a hot spot or a cold spot in the microwave sky. Importantly, the predicted feature is localized. A cosmic texture does not have to alter the entire CMB. It can produce one broad circular temperature feature. That immediately made textures interesting once the cold spot had been identified. In 2007, researchers including Maria Cruz, Neil Turok, Patricio Vielva, Enrique Martinez Gonzalez, and Michael Hobson tested the idea directly. They compared the observed cold spot with a theoretical temperature profile expected from a collapsing texture. The fit was surprisingly reasonable. The characteristic angular size was compatible, the amplitude was compatible, and a Bayesian analysis gave the texture interpretation enough support that the researchers argued it deserved serious consideration. Their best-fitting model corresponded to a symmetry-breaking energy scale of roughly 8.7 times 10 to the 15th gigaelectronvolts. That is an absurdly large energy scale by laboratory standards. The Large Hadron Collider reaches collision energies of thousands of gigaelectronvolts per particle interaction. The energy scale associated with the proposed texture would be trillions of times higher. So if the cold spot really were produced by such an object, we would effectively be using ancient microwave photons to investigate physics that no terrestrial accelerator could approach. It would be a very economical experimental arrangement. The universe performs the high-energy physics. We provide the telescope. Unfortunately, the universe has not provided a signed certificate saying that this is what happened. The texture model has a major advantage over some other exotic proposals because it predicts a fairly specific temperature profile. It also has another interesting property. If textures form in the way these models suggest, there should not necessarily be only one. A network of texture events could occur as the universe evolves, producing a population of hot and cold features with different angular sizes. Most would be relatively small or weak. Only a few large ones would be detectable in CMB maps. Early calculations suggested that seeing roughly one texture as large as the cold spot over the observable sky would not be unreasonable under certain parameter choices. That is certainly more satisfying than proposing a phenomenon that should produce thousands of obvious scars when only one is visible. Researchers therefore searched for additional texture candidates. Some analyses identified other possible hot and cold features, but none developed into an accepted detection. Planck later placed strong limits on the overall contribution that topological defects could make to the CMB. This is an important constraint. There was a time when cosmic defects were considered possible primary sources for the density variations that eventually created galaxies. Modern CMB observations do not support that picture. The acoustic peak structure measured by WMAP and Planck strongly favours primordial fluctuations of the kind generated in inflationary models. Defects, if they exist, can contribute only a small fraction of the total CMB anisotropy. Planck's 2015 analysis found no evidence for cosmic defects and tightened limits on global textures as well as several varieties of cosmic strings. That does not mean one isolated texture is mathematically impossible. It does mean textures cannot be freely added in large numbers without disturbing the rest of the microwave sky. Any texture explanation for the cold spot, therefore, has to fit inside those broader limits. There is also the problem of independent evidence. If the cold spot is a texture, ideally some additional observable would distinguish it from an ordinary Gaussian temperature fluctuation. Temperature alone can be deceptive. A rare random fluctuation can accidentally resemble a theoretical template. Researchers have examined polarization and other signatures in an effort to make the distinction sharper. So far, there has been no decisive companion signal that identifies the cold spot as a texture. The model remains possible, it is not established. That has not stopped physicists from considering other ways in which the early universe could create one unusual region. One family of ideas modifies inflation itself. The simplest inflationary picture treats the field responsible for inflation as behaving smoothly across our observable region. Quantum fluctuations are generated everywhere. Their statistics are nearly Gaussian. Inflation ends. The resulting density variations later appear in the CMB and grow into cosmic structure. It is an impressively successful framework. But there is no requirement that the true inflationary physics had to be simple. There may have been several fields. The potential controlling those fields may have contained bumps, steps, valleys, or other features. The path taken by the fields during inflation may have changed locally. Additional fields could have influenced how inflation ended, or how its energy was converted into ordinary particles afterward. Each of these possibilities provides ways to generate localized non-Gaussian structures. That last phrase is especially relevant. The cold spot is interesting partly because it behaves like a localized departure from the otherwise nearly Gaussian CMB. Planck found no convincing evidence for strong primordial non-Gaussianity across the sky as a whole. So any early universe explanation has to answer an awkward question. How do you produce one conspicuous strange region without making the entire microwave background strange? One proposed answer involves what is called inhomogeneous or modulated reheating. Inflation is thought to end with the energy associated with the inflationary field being transferred into particles and radiation. This transition is called reheating. Despite the name, it is not the universe warming back up after sitting beside an open window. It is the process that converts the energy driving inflation into the hot mixture from which the later universe develops. If another field influences how quickly the inflaton decays, reheating could occur slightly differently from one region to another. Usually such variations would need to remain tiny and statistically well behaved. But some models allow a secondary field to influence only a localized region. That could generate an unusually large density perturbation in one place while leaving most of the CMB nearly Gaussian. In 2014, one study developed this kind of localized inhomogeneous reheating scenario, specifically with a cold spot in mind. The idea was not that the model had been discovered in the data. It showed that early universe field dynamics could, in principle, produce a localized anomaly without requiring equally dramatic non-Gaussianity everywhere. Other researchers have proposed multi-field inflation models in which the trajectory through field space becomes temporarily deflected. This sounds abstract until we reduce it to the basic idea. Imagine inflation being controlled not by one variable, but by several. The evolving universe follows a path through those variables. Normally that path is smooth. Now suppose the underlying potential contains a localized feature. When the inflationary trajectory encounters it, the path can bend or scatter. Quantum fluctuations associated with one field can then be converted into density fluctuations in another. Under some constructions, this process can generate localized cold regions in the eventual CMB. One proposal called this feature scattering. It was designed to produce cold spot-like structures without relying on another bubble universe. Again, this is theoretical possibility rather than observational confirmation. The models introduce additional fields and parameters. Once extra freedom is added, fitting one unusual feature becomes easier. The real test is whether the same model makes additional predictions that can be checked elsewhere. This is a recurring difficulty in exotic cosmology. A model designed after the cold spot is known can often be adjusted until it produces something resembling the cold spot. That resemblance is not enough. Scientists want predictions that were not built into the fit. Perhaps the model should also produce a particular signal in polarization. Perhaps it should create a corresponding feature in the CMB power spectrum. Perhaps it predicts other spots of known sizes. Perhaps it changes the distribution of galaxies. The more independent test it survives, the more seriously it can be taken. Otherwise, cosmologists are simply designing increasingly sophisticated ways to draw a blue circle. Another possibility involves primordial voids. These should not be confused with the Eridanus supervoid. Eridanus is a comparatively recent structure produced as galaxies, and matter evolved over billions of years. A primordial void would originate much earlier, potentially during inflation or another early universe process. If a large underdensity already existed near the surface of last scattering, it could directly affect the CMB temperature pattern. This avoids the weakness of the late-time supervoid explanation, because the effect would not depend only on the small integrated Sachs-Wolf temperature shift accumulated during the photon's later journey. Instead, the abnormal density structure would be part of the conditions imprinted near the time the CMB formed. The price is that producing such an enormous primordial feature requires physics beyond the simplest Gaussian inflationary model. Once again, the anomaly is not removed, it is moved earlier. The question changes from why is there a giant supervoid in Eridanus to what happened during inflation to generate such a large localized perturbation. That might be worthwhile if the model explains additional observations. Without those additional successes, it is difficult to prefer over a rare random fluctuation. There have also been attempts to change the late-time physics instead of the early universe. The Eridanus supervoid has the correct general location and the correct sign of temperature effect. Its main problem is that standard lambda CDM predicts an ISW signal that is too small. One response is obvious. What if the standard model is underestimating the effect? The integrated Sachs-Wolf signal depends on how gravitational potentials evolve as the universe expands. That evolution depends on dark energy and on the theory of gravity. Change either one, and the temperature imprint associated with large voids can change. Researchers have therefore considered dark energy models in which the equation of state differs from a simple cosmological constant. Others have studied modified gravity theories. In principle, these changes could make large-scale gravitational potentials evolve more strongly and increase the effect on CMB photons. This is attractive because it preserves the foreground connection. The supervoid is real. Perhaps gravity or dark energy simply makes its microwave imprint stronger than lambda CDM predicts. The difficulty is that the same altered physics must work everywhere else. You cannot quietly strengthen gravity's effect only in Eridanus and then return to standard cosmology when nobody is looking. A modified dark energy model changes cosmic expansion. A modified theory of gravity affects the growth of structure, gravitational lensing, galaxy clustering, and other observables. Those quantities have been measured. Any theory strong enough to make the Eridanus supervoid generate the entire cold spot must also survive those independent tests. Studies allowing the dark energy equation of state to vary have generally found that reasonable changes still do not allow the observed void to reproduce the full cold spot profile. The gap is simply too large. More radical modifications can create larger effects, but they also become harder to reconcile with the rest of cosmology. There is another class of explanation that once attracted attention. Perhaps the geometry of the entire universe is slightly different from what we assume. Standard cosmology treats the universe as statistically isotropic on large scales. That means there is no preferred cosmic direction. The laws and broad statistical properties should look the same whichever way you face. Some exact solutions to Einstein's equations describe anisotropic universes. One family is known as Bianchi models. Certain Bianchi Type 7H models can generate swirling large-scale temperature patterns in the CMB. When researchers fitted these templates to WMAP data, there were initially intriguing results. The templates could reduce the apparent significance of several anomalies, including features associated with the cold spot. That sounds promising until the cosmological parameters required by the best-fitting Bianchi models are examined. They are not consistent with the parameters measured independently from the ordinary CMB power spectrum. In effect, the model could improve the appearance of some anomalies only by describing a universe that conflicted with the rest of the data. Later Bayesian analyses disfavored the Bianchi explanation. It remains an interesting historical example because it shows how dangerous it can be to judge a model by whether it visually cleans up one unusual feature. A universe must explain more than one spot. Other proposals have involved unusual topology. Topology concerns the global connectedness of space. The universe could, in principle, have a geometry that causes space to wrap around on itself in ways analogous to the surface of a torus, though in 3 dimensions. If cosmic space were compact on scales not much larger than the observable universe, light could potentially travel around it along multiple paths. That might create matching patterns or unusual correlations in the CMB. Planck searched for evidence of such non-trivial topology through matched circles and other signatures. No convincing evidence was found. The allowed size of many simple compact topologies was pushed beyond the scale, where they could easily explain localized features like the cold spot. This does not prove that cosmic topology is perfectly trivial. It simply leaves no observational reason to use unusual topology as the preferred cold spot explanation. Even ordinary astrophysics has occasionally entered the conversation. A sufficiently massive galaxy cluster can distort the CMB through the Sunyaev-Zeldovich effect. Hot electrons in intracluster gas scatter CMB photons, changing their energy distribution. At some microwave frequencies, this produces a temperature decrement. Could an enormous cluster in the cold spot direction be responsible? Researchers tested that possibility early. The answer was effectively no. A cluster capable of producing a feature this large and strong would have to be extraordinary, and there is no corresponding object. The expected Sunyaev-Zeldovich contribution from realistic clusters is far too small. It also has a characteristic frequency dependence that does not match the cold spot's behavior as a primary CMB-like signal, so we can safely leave the invisible monster cluster off the main list. What remains is an unusual collection of options. A cosmic texture can produce the correct general type of localized feature, but lacks independent confirmation and is constrained by Planck's limits on defects. A bubble collision is permitted by some eternal inflation models, but has not been detected in systematic searches. Localized multi-field inflation can be designed to generate non-Gaussian cold regions, but introduces additional early universe physics for which there is no separate evidence. A primordial void moves the anomaly back toward inflation, rather than explaining why such an unusual perturbation formed. Modified gravity or unusual dark energy could strengthen the supervoid's effect, but large changes would have consequences throughout cosmology. An anisotropic universe and non-trivial topology have been investigated and are not favoured by the broader data. This may sound as though scientists are running out of ideas. In practice, it means they are doing exactly what an unresolved observation demands. You take every mechanism that might plausibly produce the signal. You calculate what it predicts. You compare it with the temperature map, then with polarization, then with galaxy surveys, then with the CMB power spectrum, then with every other measurement the model could affect. Most explanations have become less attractive. That is useful. Eliminating a theory is information. The frustrating feature of the cold spot is that no exotic model has performed well enough to force its way into the standard cosmological picture, while the ordinary explanation has never become so overwhelming that everyone stops discussing alternatives. Planck makes that tension especially clear. Its final cosmological results found excellent agreement with the 6-parameter lambda CDM model. They found no evidence requiring cosmic defects, no evidence for significant primordial non-Gaussianity, no evidence for the sort of isocurvature fluctuations that many multi-field scenarios might produce at detectable levels, no confirmed exotic topology, no accepted bubble collision. The broad theory works. The cold spot remains. That combination should change the way we interpret the mystery. If the anomaly represented a large failure of standard cosmology, we would expect additional inconsistencies to appear around it. Instead, almost every precise test of the early universe comes back remarkably ordinary. The cold spot is unusual locally inside a universe that is statistically very well behaved globally. That makes exotic explanations possible but expensive. Each one asks us to introduce some additional phenomenon primarily to account for one feature. Science occasionally requires exactly that. Uranus did not follow its predicted orbit perfectly, and the unexplained deviation eventually led astronomers to Neptune. Mercury's orbit behaved incorrectly under Newtonian gravity, and general relativity eventually provided the deeper explanation. An anomaly can be the first clue that a successful theory is incomplete, but anomalies can also disappear when better statistics arrive. They can come from systematic errors. They can result from selecting unusual features after seeing a data set, and sometimes a rare event is simply rare. That last possibility is much less dramatic than collapsing cosmic textures, multi-field inflation, changing gravity, or collisions involving other bubble universes. It also has one enormous advantage. It requires nothing that we do not already know how to produce. Gaussian random fluctuations naturally create hot and cold spots. If you generate enough simulated CMB skies, some of them contain regions that look surprisingly similar to the cold spot. The dispute is over how frequently that happens and which properties should count when deciding whether two spots are similar. So after working through increasingly elaborate physics, the investigation returns to a question that sounds almost disappointingly simple. What if there is nothing special causing the cold spot at all? Somewhere on that sky, there was always going to be a most unusual place. That simple fact may be the least exciting explanation for the cold spot, and also one of the most difficult to eliminate. Perhaps nothing collided with our universe. Perhaps no cosmic texture collapsed. Perhaps inflation behaved exactly as the standard model expects. Perhaps the Eridanus supervoid contributes a little to the temperature we measure, but is not responsible for anything especially mysterious. Perhaps the cold spot is simply what happens when random fluctuations are allowed to fill an entire sky. To understand why scientists take this possibility seriously, we need to be precise about what the word random means. Random does not mean that anything can happen with equal probability. The cosmic microwave background is not a television screen displaying uncontrolled static. Its temperature fluctuations follow a very specific statistical pattern. The standard cosmological model predicts how much variation should appear at different angular scales. It predicts correlations between different parts of the sky. It predicts the overall distribution of temperature fluctuations. Those predictions agree extremely well with observations. Within that statistical framework, though, the exact arrangement of hot and cold regions is random. The theory does not tell us that a cold patch must appear at one particular coordinate in Eridanus. It tells us how likely different types of fluctuations are. You can think of it a little like weather. Knowing the average rainfall in a region does not allow you to predict exactly which pavement will receive the first drop during next Tuesday's storm. The statistical climate can be understood very well, even though individual events remain uncertain. The CMB is similar, although the weather forecast is approximately 13.8 billion years late. If the primordial fluctuations are Gaussian, most temperature values should be fairly ordinary. Moderately unusual values occur less frequently. Very extreme values are rare, but rare does not mean forbidden. This distinction creates the central statistical problem. Imagine generating a simulated cosmic microwave background using the standard lambda CDM model. You create one full sky. Somewhere on that simulated sky, there will be a coldest region. Generate another sky, and it will have its own coldest region. Do this 1 million times, and every single simulation contains a winner in the competition for most suspicious-looking cold patch. Some winners will be modest, others will be impressive. A few will look so unusual that, if they appeared in real telescope data, someone would probably write a paper about them. The question is whether the real cold spot falls comfortably within that distribution, or sits so far out in the tail that another explanation becomes more reasonable. That sounds like something simulation should settle easily. Generate thousands of skies, analyze each one, count how many contain something as unusual as the cold spot. Unfortunately, the words "as unusual as" contain almost the entire problem. What exactly should be compared? The lowest temperature, the average temperature inside a 5-degree circle, the wavelet coefficient, the diameter, the warm ring surrounding the central depression, its approximately circular shape, its kurtosis, some combination of those properties. Each choice gives a different answer. This became especially important because the cold spot was originally highlighted using the spherical Mexican hat wavelet. That particular mathematical filter is well suited to detecting a feature with a cold center and warmer surroundings. Apply it to the microwave map at a certain scale, and the cold spot stands out strongly. Early analyses found that spots producing such extreme wavelet statistics appeared in fewer than 1% of Gaussian simulations. Depending on the precise test, some reported probabilities were only a few tenths of 1%. That certainly sounds unusual, but other researchers asked a slightly uncomfortable question. What happens if you use a different filter? Rajang and Drog and Huterer investigated this by analysing the WMAP sky using simple circular top hat filters and Gaussian weighting functions. Instead of finding the cold spot to be extremely unusual, they found no significant anomaly when comparing the coldest regions of the real map with the coldest regions in Gaussian simulated maps, using those alternative filters. Their argument was not that the cold spot had disappeared. The patch was still cold. Their point was that its dramatic significance depended partly on how the sky was being examined. The cold spot's temperature profile happens to resemble the shape emphasized by the Mexican hat wavelet rather well. That particular filter therefore produces a strong response. Random simulated skies are less likely to produce both an unusual cold region and a profile that happens to match the same filter so nicely. Does that mean the wavelet result is invalid? Not necessarily. Wavelets are legitimate tools for detecting localized non-Gaussian structures. If the physical phenomenon you are searching for naturally resembles that profile, the filter may be exactly the correct one to use. The argument is about when the choice was made. If you decide in advance that a certain physical model predicts a Mexican hat-like structure, apply that filter to new unseen data, and find a strong signal, the statistical interpretation is relatively clean. If you inspect a dataset, discover that one filter makes one feature especially dramatic, and then calculate the probability using that filter, you need to account for the fact that other filters could have been tried. This is the look elsewhere effect returning in slightly different clothing. Suppose you enter a room containing 100 clocks. You look at all of them and discover that clock number 73 shows exactly 11:11. If you had predicted beforehand that number 73 would show 11:11, that would be a curious result. If you merely searched 100 clocks for any interesting pattern, and then became excited about whichever one looked strangest, the surprise should be reduced. Perhaps one showed 12:34, perhaps another showed 2:22, perhaps another displayed your birthday. With enough opportunities, something memorable eventually appears. The CMB offers vastly more opportunities than a room full of clocks. Researchers can study temperatures, angular correlations, wavelets, hemispherical asymmetries, multipole alignments, parity, polarization, rings, disks, gradients, and many other properties. They can examine different angular scales. They can apply different sky masks. They can choose different regions. They can search the entire sky or concentrate on one hemisphere. The more possible statistics are available, the more likely it becomes that at least one will produce a low probability. This does not make the cold spot meaningless. It means its statistical significance cannot be summarized honestly by taking the smallest p-value ever reported and treating that number as the probability that standard cosmology is wrong. A p-value does not tell you that anyway. If a test gives a p-value of 0.5%, it means that under the assumptions of that test and model, results at least as extreme as the observed one appear about 0.5% of the time. It does not mean there is a 99.5% chance that another universe exists. This distinction has probably saved cosmologists from announcing several dozen parallel universes before lunch. Planck's later analyses made the situation clearer without making it simpler. The cold spot remained a real feature in Planck's much more precise maps. Its existence was robust across different methods used to separate the CMB from foreground radiation. WMAP and Planck had very different instruments and systematics, so the chance that both missions accidentally manufactured the same large feature became extremely small. The cold spot belongs to the actual microwave temperature sky. Planck's final assessment of the large-scale anomalies, however, was cautious. When individual tests are considered, several anomalies can produce results at roughly the 2 or 3 sigma level, sometimes stronger under particular statistics. But once researchers consider a broader collection of similar tests and account for the fact that these features were identified after looking at the sky, none provide strong evidence that the CMB as a whole violates statistical isotropy and Gaussianity. That phrase, as a whole, matters. A Gaussian universe can contain a strange spot. Gaussian statistics describe the population of fluctuations, not a rule requiring every region to look average. You could have one rare extreme value inside an otherwise perfectly normal distribution. Consider human height. If you gathered several million people, almost everyone would fall within an unsurprising range. A person far taller than average would not prove that human height has stopped following its familiar statistical distribution. A sufficiently large population is expected to contain extremes. The microwave sky gives us a very large population of correlated fluctuations. The cold spot could be one of those extremes. This possibility also explains why scientists use the phrase cosmic variance. At large angular scales, there are only a limited number of independent patterns available across our observable sky. We cannot reduce this uncertainty by building a better telescope. A better telescope can measure our sky more accurately. It cannot give us another statistically independent universe. If you wanted to know whether a coin was fair, you could toss it 10,000 times. Cosmologists studying the largest CMB modes have something closer to a coin that the universe tossed once. They can examine the result with extraordinary precision. They cannot ask for 9,999 additional universes to improve the statistics. Computer simulations are the substitute. Researchers use the measured cosmological parameters to generate many possible CMB realizations. Each simulation represents a sky that could have been produced under the same basic model. Our actual sky is then compared with that ensemble. This is powerful, but it cannot eliminate every ambiguity about which statistic should be considered unusual. The cold spot therefore lives in an awkward category. It is more unusual than the average feature. It is not so impossible under lambda CDM that the model clearly fails. A 2022 analysis examining the cold spot through CMB gravitational lensing described its temperature anomaly as having a p-value below roughly 1% in standard lambda CDM, while also finding evidence against the idea that a giant line-of-sight void is responsible for the full signal. That leaves the random fluctuation explanation in an unexpectedly strong position. Remove the easy foreground explanation, and you do not automatically make exotic physics more likely than chance. You simply reduce the number of competitors. Suppose the cold spot has a 1% probability under a particular standard model statistic. 1% is rare. It is also not remotely impossible. If you perform 100 reasonably independent searches, encountering one 1% event would not be shocking. The difficult part is deciding how many effective searches the CMB anomaly literature represents. There is no simple answer. Many tests are correlated. Different statistics often respond to the same underlying large-scale modes. The cold spot, hemispherical asymmetry, low large-angle power, and other anomalies are not necessarily independent discoveries. Some may partly reflect the same unusual realization of the largest CMB fluctuations. You cannot simply multiply all their p-values together and announce that the standard cosmological model has been defeated by arithmetic. On the other hand, dismissing every anomaly individually because many tests have been performed can also become too convenient. If several genuinely independent large-scale features all point toward the same physical departure from the model, their combined significance would matter. This is why some cosmologists continue to take the collection of CMB anomalies seriously. Reviews written after Planck have pointed out that several large-angle features persist in both WMAP and Planck, with individual significances often in the per-mil to percent range depending on the statistic used. The disagreement is not really about whether these patterns exist. They do. The disagreement is about how surprised we should be that our one observable sky contains them. There is a useful thought experiment here. Imagine that astronomers had never noticed the cold spot. Suppose instead that a new inflationary theory had been developed independently. The theory predicted one broad cold feature, several degrees across, with a specific temperature profile and a warmer ring around it. It predicted roughly where such features should appear statistically, what polarization should accompany them, and how many should exist. Researchers then opened a previously unseen CMB dataset and found a region matching those predictions. That would be much more convincing evidence for new physics. The theory came first, the target was clearly defined, there would be fewer opportunities to adjust the explanation afterward. The actual history happened in reverse. The feature came first. Many explanations followed. A supervoid, a texture, a bubble collision, primordial non-Gaussianity, modified gravity, unusual inflation. Once enough, theoretical models are allowed to compete. Someone can usually design one that produces a cold region. That does not make those models worthless. It means they need independent predictions. This is one reason cosmologists are often more interested in whether an explanation predicts something new than in whether it can reproduce something already known. A cosmic texture should have consequences beyond one cold spot. A bubble collision should produce a characteristic profile and polarization. Modified gravity should change large-scale structure elsewhere. A non-standard inflationary model should alter other primordial statistics. If none of those additional signals appears, the ordinary fluctuation explanation becomes increasingly attractive, simply because it requires no extra machinery. There is a principle sometimes associated with scientific reasoning called Occam's razor. It does not say that the simplest explanation is always correct. Nature has no obligation to be simple. It says, roughly, that we should avoid multiplying assumptions unnecessarily when a simpler explanation already accounts for the evidence. Lambda CDM already predicts random hot and cold regions. The cold spot is rare under some measures but permitted. To replace that explanation with a cosmic defect or another inflationary bubble, the exotic model should ideally explain something the standard model cannot explain at a reasonable statistical cost. This is where the phrase, "just a fluke," can become misleading. A fluke is not the absence of an explanation. Random fluctuations are part of the explanation. If the initial density perturbations were quantum in origin and approximately Gaussian after inflation, then a rare cold spot is a genuine predicted outcome of that physical process. The model does not predict which realization we will observe, it predicts a probability distribution. Our universe then supplies one realization. Sometimes the realization contains something near the tail. There is no requirement that reality should choose the most average possible sky. In fact, a perfectly average sky in every statistic would itself be suspicious. If every property of the CMB landed exactly at the theoretical mean, with no 2 sigma deviations anywhere, cosmologists might reasonably wonder whether someone had generated the map using the model rather than observing the universe. Random data should contain surprises. The challenge is knowing when there are too many surprises. That is the real tension behind the cold spot. It is not simply a contest between boring chance and exciting new physics. It is a test of how scientists recognize a genuine crack in a successful theory. History gives examples in both directions. Some anomalies became revolutions. Mercury's orbit could not be explained completely by Newtonian gravity. The discrepancy survived, improved observations. Attempts to explain it with an unseen planet called Vulcan failed. General relativity eventually explained the anomalous precession naturally as part of a much broader theory. That was a real crack in the old picture. Other anomalies disappeared. Particles have been reported at unexpected masses and then vanished when more data were collected. Astronomical signals have appeared significant before being traced to instruments, foregrounds, or a statistical selection. Even experienced scientists can become interested in patterns that later turn out to be ordinary fluctuations. The difference is rarely obvious at the beginning. The cold spot has already passed several tests that eliminate some mundane explanations. It did not vanish with Planck. It does not look like simple instrument noise. Standard galactic foregrounds do not remove it. The giant supervoid explanation has become increasingly difficult, particularly after gravitational lensing analyses found that the kind of huge line-of-sight structure needed to produce the full temperature feature is disfavored by the Planck lensing data. Yet none of that tells us that the Gaussian explanation has failed. Planck's overall CMB measurements remain in excellent agreement with the basic 6-parameter lambda CDM model. The mission found several statistical curiosities, especially at large angular scales, but no compelling overall reason from the data alone to replace the standard cosmological framework. That is an important fact to keep beside every dramatic cold spot theory. If this is a crack in our picture of the cosmos, it is a very small crack in a structure that is otherwise holding together remarkably well. There is one more complication. We know the cosmological parameters partly by fitting the same CMB sky containing the anomaly. When researchers generate simulations, those simulations are usually based on the best fitting model inferred from observations. This creates subtle statistical questions about conditioning, parameter uncertainty, masks, foreground cleaning, and which large-scale modes are included. Professional analyses account for these issues carefully, but there is no magic statistic that removes all judgment. Different reasonable choices can make the cold spot look more or less exceptional. That is why papers can appear to disagree while all using legitimate mathematics. One study may ask how extreme the Mexican hat wavelet coefficient is. Another asks whether the coldest disk on the sky is unusual. Another studies the radial temperature profile. Another conditions simulations on containing a wavelet spot as cold as the observed one, and then asks whether its surrounding structure is unusual. They are not always testing the same claim. Planck itself demonstrated this problem. Its 2015 anomaly analysis found very low tail probabilities for the cold spot under some wavelet statistics, while also discussing work in which different kernels reduced the significance substantially. There is no contradiction there. The cold spot matches certain definitions of unusualness much better than others. The scientific question becomes whether one of those definitions corresponds to a physically meaningful prediction, or whether we selected it because it makes our particular sky look interesting. That may be the most important question in the entire cold spot story. Not, is the spot cold? It is. Not, is the feature real? It is present in the measured CMB temperature sky. Not even, is it unusual? Under several reasonable statistics, yes. The difficult question is whether its unusualness contains information. A shuffled deck of cards can produce a remarkable looking hand without anyone cheating. But if the same remarkable pattern appears repeatedly, or if it matches a prediction made before the cards are dealt, suspicion becomes reasonable. With the cold spot, we have only one deal. That means the next progress may not come from staring harder at the same temperature map. Planck has already measured the relevant temperature anisotropies very well. Another mission making a slightly cleaner version of the same picture would not create a second independent universe. What scientists need are different kinds of information. Polarization offers partially independent modes. Gravitational lensing reveals the distribution of matter between us and the last scattering surface. Galaxy surveys map the foreground structure in 3 dimensions. Future measurements of the 21 centimeter signal from neutral hydrogen could eventually provide an enormous 3-dimensional record of cosmic structure across epochs that the CMB shows only as a 2-dimensional surface. Each additional observable asks the cold spot a different question. If it is merely a random primordial temperature fluctuation, those other data sets should behave in one way. If it came from a cosmic texture, they may behave another way. If unusual inflation created it, there may be correlated primordial signatures. If some foreground process remains undiscovered, improved maps of matter and radiation along the line of sight may reveal it. That is how a statistical curiosity becomes a physical discovery, not because one number becomes dramatic enough, but because several independent measurements begin telling the same story. For now, they do not. The cold spot may be a reminder that even a well-understood random universe can occasionally produce something that looks designed to attract attention, or it may be exactly the sort of small inconsistency that future cosmologists will look back on and wonder why its importance was not obvious sooner. There is no reliable way to decide between those possibilities by enthusiasm alone. The old temperature map has given us almost everything it can. That does not mean the cold spot has reached the end of its scientific usefulness. It means the next useful question is no longer simply whether the patch is cold. WMAP established that. Planck confirmed it with greater sensitivity. The temperature anomaly itself is not waiting for another spacecraft to notice it. What scientists need now is different information about the same region. That difference matters because the major explanations for the cold spot do not all predict the same things. A rare primordial fluctuation should leave one set of signatures. A foreground supervoid should leave another. A cosmic texture should behave differently again. A bubble collision or unusual inflationary event may produce its own pattern in polarization and surrounding structure. If several independent measurements begin agreeing with one of those possibilities, the cold spot can move from being a statistical curiosity to being a physical object or event that we understand. The first place to look is polarization. We encountered this earlier, but it becomes especially important here. The cosmic microwave background is not only a map of temperature, the radiation is also polarized. When CMB photons scattered from electrons in the early universe, the local arrangement of hotter and colder regions around those electrons produced a preferred orientation in some of the escaping radiation. The result is a faint polarization pattern across the microwave sky. This gives cosmologists a second record from the same era. Temperature tells us one thing. Polarization tells us something related but not identical. Suppose the cold spot is simply a large primordial fluctuation that was already present around the time of last scattering. That temperature structure should have developed alongside the same early universe processes that produce CMB polarization. Because temperature and polarization are statistically correlated, a primordial cold spot should be accompanied by a certain pattern of polarization around it. Not an enormous, obvious ring that anyone could see by opening a photograph. The expected signal is subtle. Scientists have to compare the measured polarization with many simulated skies and ask whether the region behaves the way an unusually cold primordial fluctuation should behave. Now consider the supervoid explanation. If most of the temperature depression were produced billions of years later by the integrated Sachs-Wolf effect as photons crossed an evolving void, the photons would become slightly colder after the original CMB polarization had already been established. That later gravitational effect changes temperature without creating the same primordial polarization correlation. In principle, then, polarization helps separate a feature made at last, scattering from one added somewhere along the journey. Planck tried this. The results were not decisive. Its polarization maps were enormously valuable for cosmology as a whole, but the signal relevant to this particular test was weak enough that the cold spot was not cleanly classified. That leaves room for better measurements. One of the major experiments now pushing CMB observations forward is the Simons Observatory in Chile's Atacama Desert. Its telescopes are designed to measure both the temperature and polarization of the microwave sky, with far greater sensitivity than previous ground-based surveys across the regions they observe. The observatory uses small aperture telescopes to study broad polarization patterns and a 6-meter large aperture telescope to measure finer structure. Its small telescopes are already taking data, while the large telescope has achieved first light and the observatory is building increasingly sensitive maps of the millimeter sky. That does not mean Simons Observatory has been built specifically to solve the cold spot. Its scientific goals are much broader. It is looking for signatures of inflation, measuring gravitational lensing, studying dark matter and neutrinos, mapping galaxy clusters, and improving our understanding of foreground radiation. But those capabilities overlap almost perfectly with several questions raised by the cold spot. More sensitive polarization measurements could test the region again. Better observations at multiple microwave frequencies could improve foreground separation. Higher resolution maps could examine smaller structures embedded inside and around the broad cold region. Most importantly, measurements of CMB gravitational lensing can tell us more about the matter lying between the cold spot and us. Gravitational lensing offers a very different kind of information from counting galaxies. Light passing through the universe is deflected slightly by matter. A galaxy cluster produces a stronger lensing effect than an empty region. Dark matter contributes, even though it cannot be seen directly. When this lensing acts on the cosmic microwave background, it subtly remaps the ancient temperature and polarization patterns. With sufficiently precise observations, cosmologists can reconstruct a map of the intervening mass. If there were an enormous hidden structure capable of producing most of the cold spot through a late-time gravitational effect, it should also affect lensing. Planck lensing data have already made an extremely large line-of-sight void explanation less attractive. Future high-sensitivity CMB lensing maps can improve that test. This is valuable because galaxy counts come with uncertainties. A galaxy catalogue tells us where luminous objects are. It does not directly show all matter. Galaxies may trace different environments with slightly different efficiencies. Dust can obscure them. Distance estimates can be imprecise. Dark matter dominates the mass budget but emits no ordinary light. Lensing does not care whether the matter is bright. Gravity bends the light either way. The cold spot foreground can therefore be examined from two directions. Count the galaxies. Measure the gravitational lensing. If both methods describe the same underdense structure, confidence in its size and density increases. If they disagree, the model of the foreground has to change. Optical surveys are about to make this much more powerful. The Vera C. Rubin Observatory has now begun its 10-year legacy survey of space and time, or LSST. The survey started in late June 2026 and is repeatedly imaging a vast area of the southern sky in 6 optical filters. Over the coming years, it will build an exceptionally deep record of billions of galaxies and their shapes. That matters for Eridanus. Instead of describing the supervoid using comparatively sparse galaxy catalogues, astronomers will have access to much larger samples. More galaxies means a better measurement of how the density changes across the sky. Multiple filters allow photometric redshift estimates, giving rough distances. Repeated observations improve calibration, and the shapes of distant galaxies can be used for weak gravitational lensing studies. Imagine trying to reconstruct a valley while standing in thick mist. A small survey gives you several scattered height measurements. You know there is a depression, but you're not sure whether it is one deep hole, several smaller depressions, or a long shallow trench. A much denser survey gives you far more points. The shape becomes clearer. This is essentially what improved galaxy mapping can do for the Eridanus supervoid. The distinction is important because the gravitational temperature effect depends not only on the total deficit of matter, but also on geometry. A short, deep void behaves differently from a long, shallow one. Several connected voids do not produce exactly the same signal as one enormous sphere. Dense structures around the edges can partly compensate for the missing matter. The redshift at which each structure lies matters because gravitational potentials evolve differently at different cosmic times. To calculate an integrated Sachs-Wolf signal accurately, researchers need more than the statement, "There seems to be less stuff over there." They need a three-dimensional model. ESA's Euclid mission provides another major piece of that effort. Euclid is surveying a large fraction of the extragalactic sky, invisible and near-infrared wavelengths, measuring galaxies across billions of years of cosmic history. One of its main purposes is to reconstruct large-scale structure and use weak gravitational lensing to study dark matter, dark energy, and cosmic expansion. Its first major cosmology data release is scheduled for October 2026. Euclid and Rubin approach the problem differently. Rubin repeatedly images the southern optical sky from the ground. Euclid observes from space with extremely stable imaging and near-infrared information. Combine surveys like these with microwave lensing maps, and astronomers can cross-check the foreground mass distribution using methods with very different sources of error. That is exactly what an unresolved anomaly needs. One measurement saying there is a void is interesting. Several independent surveys agreeing on its precise structure are far more useful. Spectroscopy can add another layer. Photometric redshifts are efficient because astronomers can estimate distances for enormous numbers of galaxies from broadband colours. They are not extremely precise for individual objects. Spectroscopic redshifts require more observing effort, but provide much sharper distance information by identifying known spectral lines and measuring how far those wavelengths have shifted. A dense spectroscopic survey through the cold spot direction could separate foreground structures that currently blur together. Perhaps what appears to be one enormous supervoid is actually a sequence of smaller voids. Existing observations already suggest something like this. Better spectroscopy can determine their boundaries, depths, and surrounding overdensities more precisely. That would allow a cleaner prediction of the temperature signal they should produce. Then there is microwave frequency coverage. A primordial CMB fluctuation has a particular blackbody temperature signature. Several foreground processes do not. Dust from our galaxy has its own spectrum. Synchrotron emission behaves differently. Hot gas in galaxy clusters produces the thermal Sunyaev-Zeldovich effect, which changes sign depending on observing frequency. Unresolved radio and infrared sources add other signals. WM, AP and Planck already used multi-frequency observations to show that a simple foreground explanation for the cold spot is unlikely. Future instruments can improve those limits. This may sound like scientists checking something that has already been checked. They are. That is not wasted effort. The more exotic the alternative explanations become, the more important it is to be absolutely certain that a small, neglected astrophysical foreground is not contributing. Nobody wants to announce evidence for physics from the inflationary era, and later discover that part of the signal came from dust. Cosmology has enough paperwork without adding that particular conversation. Another possibility is to search for the predicted signatures of cosmic textures. If a texture created the cold spot, then the event should not be treated only as a convenient curve that happens to fit the temperature profile. A physical texture model predicts a population. Depending on the underlying symmetry breaking scale, smaller texture events should occur elsewhere in the sky. Some would create hot spots, some cold spots. Most would be weaker than the famous feature. More sensitive CMB maps could therefore perform population tests. Do the numbers and sizes of unusual localized regions match what a texture model predicts? Or is the cold spot alone? The same logic applies to bubble collisions. One attractive feature can always be fitted after the fact. A theory becomes more convincing when it predicts features that researchers did not use to construct it. Bubble collision models can predict boundaries, temperature gradients, polarization patterns, and a distribution of angular sizes. Improved CMB data can search for those characteristics systematically. If no additional candidates appear, the allowed rate of observable bubble collisions becomes smaller. A non-detection is useful. It tells theorists which versions of eternal inflation remain viable. Future polarization observations could become particularly important for these early universe possibilities. JAXA's Lightbird mission is being developed specifically to make extremely sensitive full-sky measurements of CMB polarization, with a primary goal of searching for primordial B-mode polarization associated with inflation. As of 2026, the mission has passed a major definition review and moved into its project preparation phase, with JAXA currently aiming for launch in the 2030s. Lightbird is not a cold spot mission either. Its main target is the broad polarization signature that primordial gravitational waves could leave in the CMB, yet a cleaner full-sky polarization map would improve our general understanding of the early universe. That matters because every exotic cold spot explanation lives inside a larger theory. If Lightbird were to detect primordial B modes and constrain the energy scale of inflation, many inflationary models would suddenly become much more restricted. Some mechanisms proposed for the cold spot could become easier to accommodate. Others might become implausible. The cold spot cannot be interpreted separately from the rest of cosmology. The better we understand inflation globally, the less freedom there is to invent local explanations. There is an even more ambitious source of future information, the 21 centimeter line of neutral hydrogen. Hydrogen atoms can emit or absorb radio waves with a rest wavelength of about 21 centimeters. Because cosmic expansion stretches this wavelength, observations at different radio frequencies can probe hydrogen at different distances and therefore different cosmic times. Future radio surveys hope to map enormous volumes of the young universe during periods such as the cosmic dawn and the epoch of reionization. The Square Kilometre Array is being developed partly to pursue this kind of science. This is interesting because the CMB gives us something close to a two-dimensional screen. We see the last scattering surface projected around us. 21 centimeter observations could eventually provide three-dimensional information about later cosmic structure across a large range of redshifts. They would not photograph the inflationary cold spot directly, but they could test whether an unusual primordial perturbation left a continuing imprint in the distribution of matter and hydrogen along that direction. If the cold spot were associated with a genuinely large primordial underdensity, some descendant structure might persist. If it were only a temperature fluctuation with no unusual later matter distribution, the 21 centimetre sky could look ordinary. These measurements are extremely challenging. Foreground radio emission is much brighter than the faint cosmological signal. Instrument calibration has to be extraordinarily precise. Still, the idea illustrates how the cold spot problem may eventually be attacked, not by making the same picture repeatedly, by examining the same region through completely different physical effects. Polarization tells us about scattering in the early universe. CMB lensing tells us about integrated mass. Galaxy surveys trace luminous structure. Weak lensing traces total matter. Spectroscopy provides precise distances. Microwave frequency coverage tests foregrounds. 21 centimetre observations may eventually trace neutral hydrogen through large cosmic volumes. Each dataset supplies a new piece of information. There is also a simpler statistical improvement that comes from better observations of the rest of the sky. The cold spot is judged unusual by comparison with the statistical properties of the CMB. If future experiments constrain primordial non-Gaussianity more tightly, they narrow the range of early universe models capable of producing localized features. If improved polarization confirms that the primordial perturbations are even more Gaussian than we already think, explanations involving special inflationary events have less room. If departures from Gaussianity are found independently elsewhere, the cold spot becomes more interesting. The context can change even if the spot itself does not. That may be the most realistic way the mystery is eventually resolved. There may never be a single observation accompanied by an alarm and a message saying "cold spot solved." Instead, one explanation could gradually become difficult to maintain. The supervoid contribution might be calculated to high precision and shown to account for only a small fraction. Polarization could become fully consistent with an ordinary primordial Gaussian fluctuation. Searches for textures might find nothing. Bubble collision limits might tighten. In that situation, the cold spot would quietly become less mysterious. It would remain unusual, but the probability that it's simply an extreme fluctuation would become the practical scientific answer. Or the opposite could happen. A future polarization map could show a pattern that ordinary Gaussian simulations rarely reproduce. A matter survey might reveal an unexpectedly extreme structure exactly aligned with the temperature feature. Another CMB anomaly might appear with the same profile predicted by a topological defect. An inflationary model developed for independent reasons might predict something remarkably similar. Then the cold spot would stop being an isolated curiosity and become evidence. That is the distinction worth watching. An anomaly alone is a question. A repeated, independently predicted pattern is a discovery. For now, the old photons continue arriving. Every microwave detector pointed toward Eridanus receives radiation that began travelling when the universe was only a few 100,000 years old. The photons themselves are not changing their story. Our ability to interrogate that story is changing. A temperature measurement gave us the mystery. Polarization, lensing, galaxy maps, and future surveys may tell us whether the feature was created near the beginning, modified on its way to us, or simply selected by chance from a perfectly ordinary statistical sky. And until those independent measurements begin favouring one explanation strongly, the cold spot remains useful for a reason that has very little to do with how dramatic it looks on a coloured map. It forces cosmologists to ask exactly what their theories predict, exactly how much evidence is needed to challenge them, and exactly how much information can be extracted from the oldest light we are able to observe. Whether the cold spot eventually turns out to be extraordinary or completely ordinary, it has already shown us something important about what we can and cannot infer from the early universe. That may seem like a less satisfying answer than another universe. It is certainly less dramatic than discovering a cosmic texture left behind by physics at an energy scale trillions of times beyond our most powerful particle accelerators. But science does not become less interesting when a mystery refuses to cooperate with its most exciting explanation. Sometimes the unresolved part is exactly what teaches us the most. The cold spot began as a statistical oddity in a map of microwave radiation. That map itself represents one of the greatest successes in modern science. Almost 13.5 billion years before WMAP and Planck were launched, photons stopped scattering constantly through the hot plasma of the young universe and began travelling freely. They crossed a cosmos that contained no solar system, no Earth, no Milky Way in its present form. Most of the galaxies we know had not yet formed. Those photons continued travelling while gravity slowly turned tiny density differences into stars, clusters, filaments, and voids. Much later, one small rocky planet developed radio telescopes capable of measuring differences in their temperature of only a few millionths of a degree. That achievement is already remarkable without adding another universe to it. When scientists examine the resulting CMB map, they find exactly the kind of structure that the standard cosmological model broadly predicts. Tiny fluctuations, a nearly Gaussian distribution, acoustic patterns left by pressure waves in the primordial plasma, a power spectrum with peaks and troughs that tell us about ordinary matter, dark matter, geometry, expansion, and the initial conditions from which structure grew. From those tiny differences, cosmologists can estimate the age of the universe. They can infer its composition. They can test whether space is geometrically close to flat. They can constrain neutrino physics. They can investigate inflation. A theory that can do all of that deserves to be taken seriously. Then there is the cold spot. One broad area toward Eridanus that refuses to look quite as comfortable as the rest. Not impossible, not necessarily revolutionary, just unusual enough to keep surviving attempts to make it boring. The first lesson it gives us is that a successful theory does not predict an average-looking universe everywhere. This sounds obvious, but it is surprisingly easy to forget. Lambda CDM is statistical. Inflationary fluctuations are statistical. The theory predicts distributions and correlations. It does not provide a pixel-by-pixel blueprint of the CMB sky. So when we observe one unusually cold region, we have not automatically found a contradiction. An ordinary Gaussian process can generate an extreme value. In a sufficiently large data set, an extreme value is guaranteed. There will be a coldest spot. There will be a hottest spot. There will be a strangest looking arrangement. If the universe were required to avoid anything surprising, it would not be random in the way the theory predicts. This is why the cold spot forces us to think carefully about probability. A feature that occurs in 1 out of 1,000 simulated skies sounds rare. But if researchers have effectively searched for hundreds of different kinds of unusual patterns, encountering one rare result becomes less surprising. Change the statistical filter and the significance changes. Define the radius differently and it changes again. Include the surrounding warm ring and you ask another question. Search only after noticing the feature, and you have to account for that choice. These are not excuses invented to protect a theory. They are part of doing statistical science honestly. The cold spot therefore teaches us that the phrase 1 chance in 1,000 is incomplete unless we also know 1 chance in 1,000 of what. That may not fit comfortably on a video thumbnail. It remains important. The second lesson comes from the failed easy explanations. When the cold spot was discovered, instrumental error had to be considered. WMAP was a spacecraft. Spacecraft have electronics. Electronics produce noise. Detectors require calibration. Data processing pipelines can introduce artifacts. Foreground subtraction is imperfect. A responsible scientist does not begin with a multiverse when a misbehaving detector is still available. Then Planck observed the same broad feature. Different spacecraft, different instruments, different frequencies, different data processing. The cold spot remained. That did not make it exotic. It made it real. This distinction has followed us through the entire investigation. The cold spot is a real temperature feature in the CMB. Its interpretation is uncertain. Next came foreground radiation. Perhaps emission from the Milky Way contaminated the region. Again, the multi-frequency data did not support a simple foreground explanation. Then came the supervoid. This was arguably the most satisfying conventional possibility. A huge underdensity exists in roughly the same direction. CMB photons crossing evolving gravitational potentials can change temperature through known general relativity. A cosmic void should produce a cold imprint. Everything seemed to fit, until the calculation was performed carefully. The Eridanus supervoid appears capable of contributing to the observed temperature depression. Under standard lambda CDM, it does not seem capable of producing the entire cold spot. The expected effect is too small. That result teaches another useful lesson. Correlation on the sky is not the same as causation. Two unusual features can align without one fully explaining the other. The supervoid may contribute. The primordial CMB may already have been cold in that direction. The final temperature could be a combination. Or the alignment could simply be another coincidence. The universe contains an enormous number of structures. Some of them will overlap when projected onto a two-dimensional sky. Once the conventional explanations became less complete, theorists moved earlier in cosmic history. That is where things became stranger. Cosmic textures, localized inflationary events, primordial voids, non-Gaussian fluctuations, bubble collisions. Each proposal began with a legitimate physical idea. Certain high-energy symmetry-breaking transitions can produce topological defects. Some inflationary theories contain additional fields or localized features. Some forms of eternal inflation permit bubble nucleation and collisions. There is mathematics behind these possibilities. Researchers can calculate approximate CMB signals. They can compare those predictions with data. That is very different from inventing a story with no test. But none of those models has acquired the independent evidence required to become the accepted explanation. This matters especially for the bubble universe idea. The cold spot is often linked publicly with the possibility of another universe because the connection is irresistible. An enormous cold circle in the oldest light. A theoretical model in which inflation creates multiple bubble regions. A collision that could leave a disc-shaped CMB signature. Put those ingredients together and the story practically writes its own headline. The evidence does not go that far. Systematic searches for bubble collision signatures have not found a convincing detection. The cold spot does not contain an established polarization signature identifying it as a collision. There is no independent observation proving another bubble universe exists. So the responsible statement is narrow. Some versions of eternal inflation predict bubble collisions. Such collisions can, in principle, produce localized CMB features. The cold spot has motivated tests of those ideas. It has not confirmed them. That may feel cautious to the point of disappointment. It is also how we avoid turning a scientific anomaly into mythology. Cosmic textures occupy a similar position. They can produce localized hot and cold CMB features, with profiles that have been compared seriously with the cold spot. But Planck places strong limits on the overall contribution of cosmic defects. No independent population of textures has been discovered. No additional observation identifies the cold spot specifically as one. Possible is not the same as preferred. Preferred is not the same as demonstrated. Those distinctions become increasingly important as the physics becomes more dramatic. Then we return to the least dramatic option, a random fluctuation. After all the supervoids, phase transitions, changing gravitational potentials, inflationary fields and neighbouring bubbles, perhaps the answer is simply that our universe happened to contain an unusually cold primordial patch. That possibility can sound almost insulting after so much investigation. Imagine spending years building satellites, running simulations, mapping galaxies, reconstructing dark matter and calculating high-energy field theories only to conclude that the universe rolled an uncommon number. Yet that would not make the research pointless. Quite the opposite. To justify calling the cold spot a random fluctuation, scientists need to eliminate or constrain the alternatives. They have to demonstrate that instruments are not responsible. They have to test foregrounds. They have to map the supervoid. They have to calculate gravitational effects. They have to compare temperature and polarization. They have to search for textures and bubble collisions. By doing that, they improve our understanding of the CMB, even if the final answer is ordinary. An anomaly is useful because it stresses the model. It asks the theory to explain not just average behavior, but its extremes. There is another thing the cold spot teaches us. We have only one observable universe. That limitation sounds almost trivial until you try to do statistics with it. If scientists want to understand a population of stars, they can observe millions of stars. If they want to study galaxies, there are billions available. If they want to test particle decays, they can produce enormous numbers of particles. But when the question concerns the larger scale statistical properties of the entire observable cosmos, there is one sample, one sky, one realization of the primordial fluctuations. We cannot ask what the CMB would have looked like if inflation had produced a slightly different random arrangement. We can simulate alternatives. We cannot observe them. This limitation is called cosmic variance, and no improvement in detector sensitivity can remove it completely. That means some questions about the cold spot may never receive a perfectly clean answer. Suppose every future test behaves exactly as standard cosmology predicts. The foreground structure is mapped precisely. It accounts for 20% of the temperature anomaly. Polarization is consistent with a primordial Gaussian fluctuation. No texture population appears, no bubble collisions appear, no unusual inflationary signal is found. At that point, scientists would have excellent reason to treat the cold spot as an uncommon fluctuation, plus perhaps a modest foreground contribution. But nobody could travel to another realization of the universe to prove that interpretation experimentally. The conclusion would be statistical. That is normal in cosmology. We infer the history of the universe from the evidence available inside it. Sometimes the evidence allows astonishing precision. Sometimes it leaves a probability distribution. The cold spot sits closer to the second category. There is also a broader point about the Big Bang. Calling the cold spot a Big Bang scar is useful as an image, but it should not be taken literally. The cosmic microwave background did not emerge at the instant of the Big Bang. It was released roughly 380,000 years later. The cold spot is not a wound in space. It is a region where the microwave temperature is lower than average across a particular angular scale. If its origin is primordial, the conditions that produced it could trace back much earlier than recombination, potentially even to inflation. If its origin is partly foreground, part of the signal may have been added billions of years later. The word scar captures the idea that ancient events can leave measurable traces. Physics is more precise than the metaphor. What the CMB really gives us is a fossil record. Not a fossil in the sense of a bone preserved in rock, but information preserved because photons began travelling freely and retained a record of the conditions around them. Those photons show us that the early universe was extraordinarily uniform. They also show that it was not perfectly uniform. That second fact is why anything exists around us today. If matter had been distributed with absolute smoothness, there would have been no slightly denser regions for gravity to amplify, no clusters, no galaxies, no stars. The tiny fluctuations in the CMB are therefore not imperfections in an otherwise tidy picture. They are essential. The cold spot is an extreme member of a population of irregularities that eventually made structure possible. Whether it requires extra physics depends on whether its extremeness exceeds what those ordinary primordial processes reasonably produce. So far, the answer remains uncertain. This is why the anomaly does not overthrow the Big Bang model. The existence of the CMB itself is powerful evidence for a hot early universe. Its black body spectrum matches that prediction with extraordinary precision. Its acoustic structure matches a universe containing ordinary matter, dark matter, and dark energy. The cold spot sits within that successful framework. It challenges details of the statistical realization, not the basic fact that the universe evolved from a hot, dense, early state. Even if the cold spot eventually turns out to involve unusual inflationary physics, that would refine our picture of the beginning rather than erase it. The same is true of inflation. The cold spot alone cannot tell us whether inflation occurred. It cannot tell us which inflationary model is correct. But it gives theorists a localized test. Any model proposed to explain it must also fit everything else. That requirement is extremely restrictive. You cannot create one cold spot at the cost of ruining the acoustic peaks. You cannot introduce large non-Gaussianity everywhere when Planck sees a nearly Gaussian sky. You cannot produce dozens of textures if observations permit only a small defect contribution. You cannot strengthen the integrated Sachs-Wolf effect dramatically without checking what the same change does to galaxy clustering and cosmic expansion. The rest of the universe keeps the explanation honest. That may be the cold spot's most valuable scientific role. It sits at the edge of an extraordinarily successful model and asks whether the edge is fraying. So far, we cannot say that it is, but we also cannot completely explain why this one region looks the way it does. Future observations may eventually make the answer mundane. That would be a success. They may reveal something genuinely unexpected. That would also be a success. Science does not require the universe to choose the entertaining option. It requires the evidence to choose. As we reach the end of this investigation, think back to what the cold spot looked like at the beginning. A blue region on a microwave map. That was all. From that one feature, we had to learn what the cosmic microwave background actually is. We went back to a universe filled with plasma, when light could not move freely. We watched neutral atoms form, and the cosmos become transparent. We followed those photons across billions of years. We saw how tiny primordial fluctuations became galaxies and voids. Then, WMS Ossipi mapped the microwave sky in enough detail for researchers to notice one unusually broad cold feature. Planck checked it. The feature remained. Astronomers searched the foreground and found the Eridanus supervoid. Gravity could connect the two, but not strongly enough to provide a complete answer. That sent us toward much earlier physics, textures, inflationary irregularities, bubble collisions. Each one offered a possible mechanism. None supplied the missing proof. Eventually, after travelling through some of the strangest ideas in theoretical cosmology, we arrived back at statistics. Maybe the spot means something. Maybe it does not. That may sound as though we have travelled a very long way to arrive where we started. But we are not in the same place. We now know which explanations are weak. We know which observations would matter. We know that a simple instrumental error is unlikely. We know that the supervoid exists but cannot easily account for the entire temperature decrement. We know that exotic mechanisms are possible without being supported strongly enough to claim. And we know that standard cosmology can produce rare features even when the model is correct. That is progress. Uncertainty becomes more useful when its boundaries are understood. The cold spot also provides a good reminder that the early universe is not something science understands from one argument. Our picture of it comes from many independent pieces: the expansion of space, the abundance of light elements, the cosmic microwave background, galaxy clustering, gravitational lensing, supernovae, the distribution of matter. Each measurement tests a different part of the story. An anomaly in one dataset deserves attention precisely because the larger framework is so successful. If several independent observations begin failing in the same direction, then we may have found a genuine problem. If they continue agreeing while one patch remains unusual, statistical chance becomes easier to accept. The next generation of observations will continue making that distinction. Simon's observatory is improving microwave measurements and lensing maps. Rubin has begun building a vast optical survey of the southern sky. Euclid is mapping galaxies and dark matter over enormous cosmic volumes. Future polarization missions such as Light Bird will test the physics of inflation much more directly than the cold spot can by itself. None guarantees an answer, but each reduces the number of places the answer can hide. Perhaps several years from now, the cold spot will be discussed mainly as an interesting statistical lesson. Perhaps improved foreground maps will reveal a contribution we underestimated. Perhaps polarization will favour a primordial origin. Perhaps a completely unrelated discovery in high-energy physics will make one of the exotic models suddenly seem less exotic. Scientific mysteries can change not only because we observe the mystery itself again, but because the rest of science catches up around it. For tonight, the most accurate answer remains less dramatic than the title. There is a large, unusual cold region in the cosmic microwave background. We do not have a universally accepted explanation for why it is as extreme as it appears under certain statistical measures. A giant foreground supervoid does not seem sufficient under standard cosmology. There is no convincing evidence that another universe produced it. There is no confirmed cosmic texture, and a rare primordial fluctuation remains entirely possible. That is where the evidence stands. If you are still awake, you have now followed one patch of microwave radiation from the early universe through statistics, galaxy surveys, relativity, inflation, and some of the stranger corners of theoretical physics. And if you fell asleep somewhere around the integrated Sachs-Wolf effect, that is also a perfectly reasonable response. The photons will continue arriving tomorrow. The cold spot will still be there. Scientists will keep measuring the sky around it, not because they already know that something extraordinary happened there, but because they do not. That difference is what makes it worth studying. If you enjoyed this slow journey through the oldest light in the universe, you can leave a like and subscribe to Science for Sleep. And wherever you are listening from, you can close your eyes without worrying that you need to solve the cold spot yourself. For the moment, neither does anyone else. Sleep well.